hydrogen ions and gain electrons forming Mn plus 2 ion, and 4 water molecule is formed. To make the number of electron loss and gain equal, so we will multiply the anodic half reaction with 5. So we can write that 5 copper ion or copper atoms oxidizes, forming 5 copper plus 2 ions and release 10 electrons, while we will multiply the cathodic half by 2 to make the number of electron equal. So we can write that 2 MnO4 minus ion and 16 hydrogen ion gain 10 electrons, forming 2 Mn plus 2 ion and 8 water molecule. So the Nernst equation for every still is written as E is equal to E naught minus 2.303 RT over NF and log of Q. As we know that 2.303 RT over F is equal to 0.0592 volt. Putting this value in the above equation, we can write that E is equal to E naught minus 0.0592 volt over N, where log of Q is equal to the concentration of the copper ions raised to the power 5 divided by the concentration of Mn2 plus ions raised to the power 2. Now in the first case, if the concentration of copper ion is reduced by a factor of 100, so we can write the equation that E is equal to E naught minus 0.0592 volt, where N is the number of electron lost and gained. So in the above equation we see the number of electron is 10, and log of the concentration of copper ion is reduced by a factor of 100, so it is minus 100 as the concentration has been reduced. We can also write for the copper ion that the concentration has been reduced by a factor of 100. Simply we can also write that it has been reduced by a 10 raised power minus 2 for the copper ion raised to the power 5, where there is no change in the concentration of manganese, so we take it 1 square. It is 1 molar. So calculating this equation, we can write E is equal to E naught minus 0.0592 volt divided by 10, where log of 10 raised power minus 2 multiplied by 5, so it is equal to 10 raised power minus 10. We can also write this equation in the form that E is equal to E naught minus 0.0592 volt divided by 10, where it is the principle of log that the power is equal to base, so minus 10, and log of 10, where log of 10 is equal to 1, so we omit log of 10. So we can write the equation that E is equal to E naught. We multiply both the minus signs because they are in multiplication, so we can write plus, and we cut the 10, cancel with each other, so 0.0592 volt. So when we reduce the concentration of copper ion by a factor of 100, the voltage of the cell will be increased by a 0.0592 volt. On the other hand, if we write the equation for the manganese and we reduce the concentration of the manganese ion, so the equation will be like this, that E is equal to E naught minus 0.0592 divided by 10 and minus log of, now there is no change in the concentration of copper ion, so we write it 1 power 5, and the concentration of manganese ion has been reduced by a factor of 10, so 100, so we can write 10 raised power minus 2, and we taking the square of that. So writing the equation, we write E is equal to E naught minus is equal to E naught minus 0.0592 divided by 10 minus log of 1 divided by 10 raised power minus 4. E is equal to E naught minus 0.0592 divided by 10 multiply by log of 1 over 10 raised power minus 4 is equal to 4. So E will be equal to E naught minus, so multiplying 0.0592 with 4 and divide by 10, we get the answer 0.0236 volt. So by reducing the concentration of manganese ion by a factor of 100, the potential of the cell will reduce by 0.0236 volt.
So in this problem, we are given with a galvanic cell and its standard cell potential. We have to find the pH of the solution in the anode compartment. So to do that, first we have to write down the cell reaction from the cell notation given, and then from there we'll have to calculate the cell potential for the anode compartment or the hydrogen compartment, and then we have to use the Nernst equation to find out the pH of the solution in anode compartment. So let's first write down the reaction equation from the cell notation, and the reaction equation will be hydrogen gas reacting with lead 2+ ion, and this will give us solid lead and hydrogen ion. So this is the cell reaction for the cell given, and the cell potential for this cell would be the standard cell potential for the anode compartment, and that would be from hydrogen to hydrogen plus, so from here to here, and we will add up the cell potential for the cathode compartment. That would be the cell potential for, or the standard reduction potential of Pb2 plus 2Pb. So this value is given as 0.28 volt. We have to find out this value. So EH2 to H plus, and we can find out this value from the chart, and from the chart we can see that the standard reduction potential for lead 2 plus 2 lead is minus 0.13 volt. So now we got out these two values. If we just do the calculation, we will get the cell potential for the anode compartment, and this will give us a value of 0.41 volt. So this is the cell potential for the anode compartment. Now we have to find out the pH of the solution in the anode compartment, and for that one we'll just utilize the Nernst equation. And as you know that for writing down the Nernst equation for the anode compartment, let's first write down the half cell reaction of the anode compartment. So the half cell reaction here would be so this is the half cell reaction for the anode compartment here, and we will write down the Nernst equation for this, and it will be cell potential of H2 to H plus, and so this is our Nernst equation. So it will be equal to standard cell potential for this half cell minus, we'll just write down the formula as 0.0592 volt over the number of electrons which is transferred in the process, and we see that the number of electrons transferred in the process or reaction is 2, so we'll place it 2 here, and then we will take the log of H plus ion concentration, and since the H plus ion concentration here has a coefficient of 2, so we'll place 2 here, and at the bottom we'll get the pressure of the hydrogen gas. It will come from here, and if we just take this, so this is the log of H plus ion square by the hydrogen pressure. So now we know all the values here, as we know that so we know this value as 0.41 volt. So this value is basically 0 if we look at the standard reduction potential charge. The value for hydrogen gas to hydrogen plus ion, the standard reduction potential is 0 for that. And if we just calculate this part, we will have to let's just write down it for now. Over 2 times log of, let's see, place of the value for, we'll place the value for the hydrogen pressure, which is 1, and Then if we just calculate the entire thing, we can get the value of the log of H plus as equal to, if we solve this equation, we will get 0.41 volt equal to 0.0592 pH. So we can write another line in between here. So we can make it 0.592 volt over 2, and we'll write down this one as 2 log of H plus. And now, as you know, that log of H plus is the pH, so this is our pH value. So if we just solve this equation, we will get the pH value of this as 6.92, and this is the pH of the anode compartment, or the pH of the solution in the anode compartment of the cell given. So in this problem, we are given with a cell reaction, and we are asked to find out the equilibrium constant for this cell reaction. So to do that, what we have to do first is we have to set up a relation between the equilibrium constant and the standard cell potential, because the information given here, if you want to find out the equilibrium constant from the information, we have to set up the relation between the standard cell potential and the equilibrium constant, and the relation is as follows. The standard cell potential is equal to 2.303 RT over NF times log of K, where K is the equilibrium constant and A naught is the standard cell potential. And since we are asked to find out the value in 25 degrees C, as we know that at 25 degrees C, we have a value for this part, which is 0.0592. So we can rearrange this to write down the, or find out the equilibrium constant value, and this will give us N E naught over 0.0592 volt. So now we have to know the standard cell potential value, and we have to know the value of N. If we know these two values, we can find out the equilibrium constant. So to find out the value of standard cell potential, let's write down the half cell equations, and from there we'll be able to find out the entire cell potential. So our anode half reaction here would be Fe2 plus, in aqueous form it will become Fe3 plus by donating 1 electron, and the standard cell potential for this half reaction is equal to minus 0.77 volt. And then for the cathode half reaction, we have oxygen reacting with 4 hydrogen. It will require 4 electron to give us 2 water molecule. So as we see that we need 4 electron to reduce the oxygen, and so that means we'll have to multiply the first equation by 4, so that we'll get 4 electron here. So if we just write this as 4. So it will be 4 and then 4 here and 4 here. And the standard cell potential for this reaction is minus 0.77 volt. So if we now just sum up these two values, so this 4 is with this, so it is 4 AP. So if we now add them up, we'll get 4 Fe2 plus oxygen plus 4 H plus, and we will cut off these electrons, and on the right hand side we will get 4 Fe3 plus in aqueous plus 2H2O, and then the overall cell potential will be the summation of these two. So the overall cell potential is minus 0. Okay, so the standard cell potential for the standard cell potential for this reaction is 1.23 volt. So now if we just sum them up, we'll get a value of 0.46 volt. So this is the standard cell potential for the reaction given, and now we just have to plug in these values in the formula here, and we know the value of N. The value of N here is 4 because we have 4 electrons transferring in between. So if we just plug in the values, we'll get log of E naught, log of K give us 4 times 0.46 over 0.0592, and this will give us a unitless number of 31.08. And then if we take the antilog of this equation, we will get K is equal to 10 to the power 31.08. So this is the equilibrium constant for the cell given. So in this problem, we are given with a redox reaction which involves the transfer of 2 moles of electrons, and we are given the equilibrium constant of this reaction. We have to find out the standard cell potential for this redox reaction. So let's first, to do that, we have to know the relationship between the standard cell potential and equilibrium constant, and we know that the relationship between these two is log of standard potential. The log of equilibrium constant is equal to number of electrons involved in the reaction or transferred in the reaction times the standard cell potential over 0.0592 volt. So this reaction equation is valid at a temperature of 25 degrees C. So we are given the number of electrons involved in a redox reaction, and we are given the equilibrium constant value. We have to find out the standard cell potential value from here. So if we just plug in the values we are given with, we can get, so we are given the value of equilibrium constant as 1.8 times 10 to the power minus 5, and we are given the value of N as 2, as the number of electrons transferred is 2. So if we just plug in these values, we will get log of 1.8 times 10 to the power minus 5 and on the right hand side we'll get 2 times the standard cell potential and over 0.0592 volt. And then from here we can get the value of E naught as, if we just solve this equation, we'll get the value of E naught as minus 0.140 volt. So the standard cell potential for this redox reaction given is minus 0.140 volt.
In Leclanche cell, which is also called dry cell, the following reaction occur at electrode at anode. As we know, at anode always oxidation take place, so zinc metal is oxidizes into Zn2 plus ion and release 2 electron. On the other hand, at cathode, the manganese dioxide MnO2 in the presence of ammonium ion NH4 plus ions gain these 2 electron and is reduced, forming Mn2O3 molecule, where the manganese has been reduced from +4 oxidation state to +3 oxidation state. At the same time, ammonia is formed and a molecule of water is formed. In case of alkaline cell, at a node, zinc react with hydroxyl ion from the alkali, so zinc is oxidized, forming Zn zinc hydroxide, and 2 electrons are released. At cathode, the manganese dioxide in the presence of a water molecule gain these 2 electron, forming Mn2 manganese ion form Mn2O3 molecule, and 2 hydroxyl ions are produced in the reaction. Here the manganese from +4 oxidation state has been reduced to +3 oxidation state. In case of nickel cadmium battery, at anode, cadmium is oxidized, taking 2 hydroxyl ion from the base. It is oxidized to Cd plus 2 ion, where it reacts with the hydroxyl, forming Cd cadmium hydroxide, and 2 electrons are released by the cadmium in this process. At cathode, nickel at cathode, the reduction of the nickel take place where nickel oxygen hydroxide NiOH in the presence of water molecule gain an electron, forming nickel hydroxide, hydroxyl ion is formed. To make the electron loss and gain equal, we will multiply the cathodic reaction with 2. The whole reaction will be multiplied by 2, so we will make the loss and gain of electron equal. In case of lithium battery, at anode, X number of lithium atom oxidizes into X number of lithium ion and give X number of electrons. At cathode, manganese dioxide react with the X number of lithium ion and also gain the X number of electrons, forming LiX MnO2 complex. In case of lithium ion battery, at anode, graphite anode, LiXC6 oxidizes, forming XLi ions plus 6 carbon atoms and give X number of electrons. At cathode, Li1 minus X COO2 react with XLi ion and gain the X number of electron, forming LiX COO2 complex.
In this problem, we are asked to find out the similarities and the differences between a battery and a fuel cell. So the basic similarity between a battery and a fuel cell is both of them are galvanic cells. That means they convert chemical energy to electrical energy by a redox reaction. So if you write that down, we can make 2 columns, one for battery and one for the fuel cell. And the similarity is both of them are galvanic cells. That means they convert chemical energy to electrical energy by utilizing a redox reaction. And the basic difference between these two cells is, in case of a battery, the reactants are contained in the cell. So reactants, in case of a battery, reactants are contained in the cell, but in case of a fuel cell, the reactants are not contained in the cell. They are continuously supplied from an external source. And these are two the main similarity and the difference between a battery and a fuel cell.
In case of fuel cell, the following reaction take place at electrodes. At anode, the oxidation of the hydrogen molecule take place in the presence of hydroxyl ion. It form water molecule and 4 electrons are released in the process. On the other hand, at cathode, oxygen molecule is reduced, gaining these 4 electrons in the presence of 2 water molecule. Here it form 4 hydroxyl ions. As we know that the oxidation potential of hydrogen is 0 volt, while the reduction potential of oxygen in this case is 0.4 volt. To combine both the reaction, adding both the reaction, we can cross the electrons on either side. Also the hydroxyl ions on either side, and we can cut 2 water molecules, so we can say that 2 hydrogen react with an oxygen forming 2 water molecule, and the overall cell potential E cell is equal to the oxidation potential plus reduction potential, so it is equal to 0.4 volt. In case of proton exchange membrane cell, PEM, proton exchange membrane cell, PEM. At anode, the water molecule, the hydrogen oxidizes, form hydrogen ions, and 4 electrons are released. At cathode, oxygen molecule in the presence of these 4 hydrogen ions gain the 4 electrons, forming 2 water molecule. As again we know that the oxidation potential of hydrogen is 0 volt, while in case of proton exchange membrane, the reduction potential of oxygen is 1.23 volt. Combining both equation, adding the 2 equation, we can cross hydrogen ions and electrons on either side of the equation, so we can say 2 hydrogen molecule react with an oxygen molecule, forming 2 water molecule, and overall cell potential is equal to the sum of oxidation and reduction potential, which is 1.23 volt. In case of corrosion of iron, the iron is first oxidized into ferrous ion, where it gave 2 electron. In the next step, the ferrous ion react with the oxygen molecule in the presence of hydrogen ions, where it further oxidizes into ferric ion. Here 4 ferrous ion oxidizes into 4 ferric ion in the balance equation and gave 2 water molecule. Then the ferric ion react with water molecule forming Fe2O3 monohydrated rust molecule, and hydrogen ions are formed in the reaction. So here rust is formed in this reaction. In case if magnesium is present, so the oxidation potential of magnesium is high than the iron, so magnesium is oxidized to magnesium ion and release 2 electrons. The electron released by the magnesium keep the iron Fe3 plus ion in the reduced form, that is iron. To make the reaction balance, we will multiply the magnesium and the number of electrons released by magnesium with 3, and the iron and the number of electrons gained by iron with 2, so the reaction will be balanced. In case of magnesium, when magnesium is oxidized, and release 2 electrons, the electrons are gained by the oxygen and it form water molecule. So when magnesium is present, we will find the iron in the reduced form and there will be no corrosion of iron. This is called cathodic protection.
Today we are going to be looking at the electrolysis of potassium hydroxide, and in part A we will be labeling the anode, cathode, and ion flow, and in part B we will be labeling the reaction at the anode, cathode, and overall. Let's start by understanding what electrolysis is. So this is the process of electrically splitting an electrolyte. Currently our electrolyte is potassium hydroxide, which is going to break down to give us potassium and the hydroxide ion. If we look at what the anode and cathode are in the next steps, typically in our voltaic cell equations, we noted the anode as negative and the cathode as positive. However, in this, our cathode will be negative and our anode will be positive. Additionally, at the anode, we're going to be having oxidation, and at the cathode, we will be having our reduction occurring. By looking at Leo says Ger, we can understand what's happening with our electrons. So at the anode, we are going to be having oxidation, so a loss of electrons. And at the cathode, we are going to be gaining electrons. And we're flowing from anode to cathode in terms of our electrons. Next, we are going to draw out what is going on here. So we are going to go and draw our 2 electrodes, and we are going to submerge them under molten potassium hydroxide. We're going to go ahead and label our electrode on the left as our cathode and our electron on the right as our anode. And as we have previously discussed, our cathode is going to be labeled as negative and our anode as positive. Based on the electrolysis of potassium hydroxide, it's going to break into K plus and OH minus. And due to the fact that opposites attract, K plus is going to flow towards the cathode and our ion flow for hydroxide will be towards the anode. And now we have completed part A. Next, we're going to write out our reaction equations. So we'll start with potassium at the cathode, and this is going to be a gain of electrons. So we're going to have our positive potassium ion reacting with an electron to give us elemental potassium. And this is our cathode equation. Now at the anode, we are going to have the hydroxide ion, and it's going to be losing electrons, that is, it is oxidation. And in order to see what this will split into, if we draw out our hydroxide ion splitting, it's 2 parts, oxygen and hydrogen will form H2O and O2 as compounds, and as I'm going to draw out now, we can see how the two H's and an O are going to group together, and how two O's are going to group together to form diatomic oxygen. Now we have to balance this equation as we have an uneven number of oxygen and hydrogen on either side. So to do this, we are going to put a 2 in front of H2O because this will give us an even number of oxygens to be working with. And if we are going to balance this out, we're going to write a 4 in front of the hydroxide ion on the left. We now have 4 hydroxide ions we're dealing with, so we're going to be losing 4 electrons. Now, for the overall reaction, we need to have an even number of electrons on either side of the equation so that we can cross them out. So because of this, we're going to multiply our cathode reaction by 4. And then we will be able to write our overall reaction. So it's 4K plus 4OH minus. That will give us 4 potassium plus oxygen plus 2 H2O. And that is our overall equation. That will be in blue. In green is our anode equation. And in red will be our cathode equation.
Alright, so problem 31 here. We're given 2 bases, and we're asked to name the base and also figure out if it's seen in DNA, RNA, or both. Okay, so the way we go about this is to just look at the different function groups or different atoms that are connected to our kind of a main ring, right? So starting with part A here, we see that we got this group sticking out of our ring, and everything else would just be hydrogens, right? The white spheres represent hydrogens. So this is an NH2 group. So whenever you only have NH2 and nothing else connected to the ring, you got an adenine, right? And also adenine would have this 2 rings connected to each other. That's also characteristic of both adenine and guanine, actually. Okay, so this NH2 tells us it's adenine. So where do you see adenine? Do you see it in DNA, RNA, or both? And we know that the only difference between DNA and RNA is the uracil and thymine. So adenine would be found in both. Okay. Okay, so part B right here, we see that we got 2 oxygen atoms connected to our ring. So whenever you see 2 oxygen atoms connected as such, immediately we think either thymine or uracil. Okay, so those are the only bases in DNA or RNA that has that kind of structure. Okay, so what tells us whether it's T or U is whether we have this methyl group right here. So this is CH3. Okay, so if you have that CH3, that means you have a thymine. So this structure right here is a thymine. If you don't have that CH3, then you have a uracil. Okay, so where do you see thymine? Do you see it DNA, RNA, or both? And we know that thymine could be found in DNA only, because in RNA we have uracil and not thymine. Okay, so those are our answers for this one. Okay, problem 40. What are functional groups? Okay, so functional groups are little compounds or molecules that are connected to a larger molecule. Okay, so it could be just one atom, okay, or it could be a compound. Okay, and it is connected to a larger molecule. Now, why are they important though? So they are important because these functional groups exhibit their own chemical properties. Okay, they have their own chemical properties. And those properties affect the larger molecule. Okay, so their chemical properties affect affect the chemistry of the larger molecule that they are connected to. Okay. Okay, so hopefully that that gave an emphasis on why we care about functional groups. Alright, so problem 41 is asking for us to describe the structure of the given functional groups. So starting here with part A. Okay, so starting with part A, we have alkene. And an alkene is characteristic of a double bond between two carbons. So we got a double bond between two carbons, and since each carbon could handle 4 bonds, we can have 2 more other things connected to each of our carbon. So that would be the structure for an alkene. Okay. Part B. Part B, we got alcohol. Okay. So part B, alcohol is characteristic of having an OH connected to a carbon. So we're going to have this carbon, and it will be connected to an O and H. Okay. So we're going to have OH connected to carbon, and as usual, that carbon could handle more bonds to other atoms. Okay. Next, part C. Part C, we have an ester. And an ester is very similar to carboxylic acid, right? Where we have a carbon double bonded to O, and then we have another oxygen right here. And as usual, it would be connected to a carbon. Okay, so what makes ester different is that instead of having hydrogen, you know how carboxylic acid would normally have H bonded to oxygen right there. So instead of having a hydrogen, we're going to have another carbon. Alright, so, and as usual, these carbons can be connected to other atoms as well. So this would be an ester. And finally, we have part D, which is amine. Okay, so amine is, as you probably remember, would have a nitrogen in it. So we have a carbon, and it will be connected to NH2. Okay, or if you want to write that out, we're going to have 2 hydrogen atoms with nitrogen. Okay, and as usual, that carbon have space for 3 other bonds. Okay, so that would be our structure for amine.
Let's propose a structure for the following conditions. For A, we need a ketone, which will have the formula C5H10O. So one possibility here is going to be CH3, CH2, C double bond O, which is our ketone, CH2, CH3. So there's one possibility for that molecule. For B, we want an ester with the chemical formula C6H12O2. So this could be one possibility, CH3, CH2, CH2, C double bond O, OCH2, CH3. So there's our ester with the formula C6H12O2. And for C, we want an amine and a carboxylic acid, which has the chemical formula C2H5NO2. So this molecule could look something like H2N, CH2, C double bond OOH for the carboxylic acid. Let's draw structures for the following molecular formulas. For A, we have C2H7N, and a possible formula can be CH3CH2NH2, and that could be a structure that can exist. For B, the formula is C4H8, and a possible structure could be CH3CH, will include a double bond here, CH3. For C, we have C2H4O, and a possible structure here is CH3CHO as an aldehyde. And for D, we have CH2O2, and a possible structure here can be HCOOH as a carboxylic acid. Let's draw the isomers of C3H8O. We can have CH3, CH2, CH2OH. We can have CH3, CH, CH3OH, and we could also have CH3, CH2, OCH3. So there would be the three isomers of C3H8O.
Problem 45, we are identifying function groups. Okay, so we have here the structure of cocaine, right? Structure of cocaine. And we are given both the line bond structure and the molecular model. Okay, so whatever is helpful, easier for you to use, let's just go for it, right? And I'm just going to use the line bond structure right here. So I'm using line bond, okay? So the way I want to do these types of problems is just to go on every carbon in the molecule, okay? So this first carbon right here is ACH3, so I'm not as interested, but it is connected to an oxygen, so maybe watch out a little bit, right? But once we get to this second carbon right here, we see that it is a carbonyl carbon, and it's actually a part of this larger function group, including the first CH3, right? So that makes it our ester. Okay, that makes it our ester. And after this carbon, we have this cyclic alkane, right? We got this ring right here. And in that ring, we see a nitrogen, okay? We see this nitrogen right here. But it's not next to any carbonyl carbon, so that makes it our amine, right? So it's not an amide. It's not an amide. Okay? And then once we get to this carbon right here, right, we see that it is connected to an oxygen, and then right next to that is another carbonyl carbon. Okay? So this group together would make another ester. Okay? And finally, we see this aromatic ring right here. We got a benzene included in this molecule, so that would be our aromatic ring. Okay? So at this point, we've gone over every single carbon in this molecule, and that's all our function groups. Okay, so problem 46. We're asked to differentiate straight chain versus branched chain alkane. Okay, so straight chain alkane is pretty straightforward. you just need to have all your carbon atoms in one straight chain, hence the name straight chain, right? So what I mean by that is, if you have any molecule at all, you'll just have all your carbons in one chain, like that, okay? Now you could have other atoms that kind of sort of work as branches, like maybe you can have a nitrogen here, an oxygen here. It doesn't really matter as long as all those carbons are in one chain, okay? Meaning you don't have any carbons sticking out out of the main chain, okay? So moving on with branch chain alkane. Well, branch chain, as the name suggests, has carbons branching out from the main chain, okay? So if you have a bunch of carbons in your molecule, okay, say this would be your main chain, there would be a carbon somewhere sticking out, okay? So maybe you got one, maybe you got two, like that, and this would be a CH2, CH3. As long as there's carbon that is outside this main chain, right? So here we see a carbon and another carbon right here. That would be a branch chain alkane, okay? But what I want to point out here, excuse me, is, say we got something like this, right? Got that, and we got maybe we got a carbon, and then maybe you'll have an O, right? OH. Okay, so that would be just an example I came up with. Okay, so now is this a branch chain alkane? Okay, so is this gonna be your main chain, and then is that gonna be your branching group? And the answer is no. Okay, remember, the main chain is the longest chain you could find. So if you find the longest chain here, it's actually the carbon. Okay, so that OH is going to be outside your main chain. So actually this molecule right here is a straight chain molecule. Okay, so try not to be confused. And I know it's not exactly a straight line, but they're all in one main chain. So hopefully that explanation was helpful.
Problem 47 is asking for us to differentiate alkane and an alkyl group. Okay, so an alkane is a molecule that contains only CH bonds. Okay, it contains only CH bonds, and all are single bonds. Okay, all are single bonds. Okay, an alkyl group is a substituent, right? It's a substituent that is derived from an alkane, okay? Derived from an alkane, okay? So if we have, for example, an ethane, right? So an ethane would be 2 carbons, right, and 3 hydrogens each, right? That would be an ethane, right? If this ethane would be connected to a larger molecule, say we have this very large molecule right here, and here we connect our ethane, right? Okay, so once that ethane is connected to a larger molecule, we don't call it ethane anymore. We call it an ethyl group, okay? So it is derived from the ethane, but since it's now connected to a larger group, we call it an ethyl group. Okay, so that's the same for every single alkane and its corresponding alkyl group. Okay. Also, one thing to notice is that the alkyl group is missing one of the hydrogens. Okay, so it's missing one of the hydrogens because it's now connected to the larger molecule. Okay, so hopefully that helped clarify the difference between the two terms.
Okay, so for problem 48, we have a molecule here that is proposed with a chemical formula of C3H9. So we're asked, why would scientists be skeptical about this molecule? Okay, so obviously this molecule is supposed to be an alkane, right? And it only has carbons and hydrogens. And the formula that we use for alkanes would be CN H 2n plus 2. Okay, so what I mean by that is if carbon has a subscript of 3, or meaning you have 3 carbons in your molecule, right? So you got C3. So N equals 3 right here, okay? So that means your hydrogen is going to have to be 2N plus 2. So 2 times 3, which is N, plus 2 would have to be 8, okay? So this is supposed to be your alkane if you have 3 carbons. And that's precisely why scientists would be skeptical about this molecule, is because it has 9 hydrogens, meaning it has 1 extra than what the carbons could handle. For problem 49, we have a set of molecules given in condensed structures, and we're asked to find what's wrong with it. So there's one thing that is wrong in each of these, and we have to find that. Alright, so starting with part A, we have a carbon double bonded to another carbon here, and we see that this first carbon has 3 hydrogens. Alright, so it has 3 hydrogens, but at the same time it's also double bonded to carbon number 2, right? So if we rewrite this, we're supposed to have carbon double bonded to another carbon with 3 hydrogens in it. Okay, and that doesn't make sense because here carbon has 5 bonds around it, and that just violates our octet rule here. And so this part right here is what's wrong with molecule A. Okay, so this part, okay, carbon 1 has more hydrogens than it can have. So part B, okay, carbon 1 is CH3 single bonded to carbon 2, nothing suspicious. Alright, and then we got carbon 2 being CH2, okay, and then bonded to carbon 1 and carbon 3, again nothing suspicious. So let's move to our double bonds here. Okay, so what I want to do is redraw this part. Okay, so we have a carbon double bonded to another carbon, and then double bonded to an oxygen. Okay, and then this carbon is bonded to, let me number our carbons so we don't confuse ourselves here. 1, 2, 3, 4, 5. Okay, so I'm drawing carbon 3 here. So this is carbon 3, and it is bonded to carbon 2. Okay, and then we have a hydrogen with it. And then carbon 4 here is bonded to CH3. Okay, so now that we drew everything, we could clearly see what is wrong here. We see a carbon, and it has 5 bonds with it, right? It is double bonded with oxygen, it's double bonded with a carbon, and then it still has this bond with CH3 right here. So that's what's wrong here. This carbon number 4 has more bonds than it's supposed to have. Okay, so part C. Let's I'm actually gonna go and start counting our carbons here, so we could talk about it easy. So 1, 2, 3, 4, 5. Okay, so carbon 1 here, right? Carbon 1 is CH3 bonded to a carbon. Nothing suspicious about that, right? Carbon 2 seems to be the same. Okay, so again, we come across our triple bond here, and I want to redraw that and see if there's anything wrong with it. Okay, so we got carbon 3, triple bond, C, and then this carbon 4 has 2 hydrogens in it, right? And then it is bonded to ACH3. And then on the left, we got CH2 bonded to carbon 3. So CH2. Okay, so is there anything wrong here? Well, yes, and it's pretty intense compared to part A and part B here. Here we got a carbon having 6 bonds, right? Got 6 bonds. It has a triple bond with carbon 3, and at the same time it still has 3 single bonds with it. So that's just whack. Okay, so that's what's wrong with this molecule. Okay, carbon 4 has just way too many bonds than it's supposed to. Okay. Alright, so we have the structure of vitamin C here on our screen, and we're asked to figure out all the functional groups that are in this structure. So again, the way I want to go about doing these kind of problems is to just go on every single carbon in the molecule and see if they have functional groups connected to them. Okay. So starting with this carbon right here, looking at everything that's connected to it, we see an OH group right here. So we got an alcohol group, right? So that's pretty much it for this carbon. Moving on to the next carbon right here, we'll look at everything attached to it. We got carbons, hydrogens, and this another OH group right here. So another alcohol group. Okay, so moving on, I'll start using a different color here. Moving on to our next carbon. There's really no immediate functional group that comes out of this carbon, so I'll go and proceed to this next carbon right here, which is a part of an alkene, right? So this would be an alkene. Alright, so, and then in this alkene, we see 2 alcohol groups connected to it, right here, okay? So, this is an alcohol group, this is also an alcohol group, okay? And then moving on to our last carbon right here, we see that this is actually part of an ester right here, right? With these kinds of functional groups, we have to be a little bit careful because sometimes it just looks like a carbonyl group, but we see that it's actually an ester, right? So this is an ester, a cyclic ester to be exact. because it is part of a ring. Okay, so at this point we've gone over every single carbon in our molecule, and I think we've got all our functional groups. Alright, so problem 50, we're naming some alkanes, right? Okay, so let's go for it, starting with part A here. So again, first step is to find the longest chain we could find, okay? So looking at the structure, this seems to be the longest chain, right? And next is we number according to where we have the first branch point. Okay, so I think it's pretty clear that the first branch point is closer if you count from the right instead of from the left. Okay, because if you count from the left, this would be your first branch point. But if you count from the right, this is your first branch point, and this is just closer to the end. So, hopefully I explained that well, but anyways, let's go ahead and count. Got 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so we got 8 carbons, meaning we have an octane, right? We got an octane for 8. Next is, let's go and find our alkyl groups, okay? So here on carbon 3, we have a methyl group. So we have 3 methyl, okay? And on carbon 4, we have an ethyl group, okay? So we have CH2, CH3, which is ethyl. Okay, so we got 4 ethyl. Okay, so now that we have that, we can go ahead and combine every information that we have. Okay, so we go by alphabetical, and since E goes before M, we start with 4 ethyl. So we got 4 ethyl, 3 methyl octane. Okay, so 4 ethyl, 3 methyl octane. Next, part B. Again, find the longest chain, and I think this would still be our longest chain. Alright, and as usual, it looks like the first branch point is closer to the right side. Okay, so it's closer if we count from the right side. So let's go ahead and count. Got 1, 2, 3, 4, 5, 6, 7. Okay, we have 7, meaning we have a heptane. Okay, we got a heptane. Let me box this answer from part A so we know it's separate. Okay, so we have a heptane. Next is we look at our branch points. Okay, so we see that on carbon 2 we have a methyl group. So we have 2 methyl. And next on carbon 4 we have this 3 carbon chain, which is an isopropyl group. So we got 4 isopropyl. Okay. Alright, so hopefully you remembered what isopropyl looked like. So finally, we've gone over all the branch points, and we could combine all the information we have. Okay, so I goes before M in the alphabet, so we get 4 isopropyl. Oops. Isopropyl, 2 methyl heptane. Okay. Alright, so that's for part B. Going for part C, I want to do this on the left side since we're kind of running out of space here. Okay. It looks like this would be our longest chain, right? And this time, I think the branch point is closer from the left side. We can't really confirm that. I think we just have to count from both sides and see. Okay, so we got 1, 2, 3, 4, 5, 6, 7, and if we count from the left side, 1, 2, 3, 4, 5, 6, 7. Okay, so the first branch point is always, looks like either way, you're going to have it on carbon 2 first. But what makes it different is that this carbon has 2 methyl groups in it, right? So it has 2 methyl groups. Let me remove that. And if we count from the left, or sorry, if we count from the right, if we follow the green counting system, we're going to end up having 2 methyl groups on carbon 6, right? But if we count from the left, if we follow our orange counting here, we're going to have our 2 methyl groups on carbon 2, okay? So remember, we still want the least kind of numbers as possible in our naming. So if we follow green, we're going to end up with let me get our highlight here, 2 and then 6, 6, right? But if we do the orange counting, we're going to have 2, 2, and then 6. So having 2, 2, 6 would be better. In fact, that would be the only correct way. Okay, so let's start counting from the left then. Got 1, 2, 3, 4, 5, 6, 7, right? Since we have 7, that means we have a heptane. Okay, and now on carbon 2, as we mentioned, we got 2 methyl groups. Okay, so we got 2 methyl, and I'm just gonna separate them for now. Well, we're gonna combine this later. And we also have that methyl group on carbon 6, so we got 6 methyl. So this is what I'm talking about earlier. If we counted from the right going to the left, we're gonna end up having 2 methyl, 6 methyl, and then another 6 methyl. So if you add these, that's pretty much how I remember it. If you add these, this would be a larger number. It's going to be 14. If we add this is only 10. So we want this, okay? We want the lower number. All right, so at this point, I think we have everything that we need, so we could combine our information. Okay, so we have all methyls. So this is going to make a trimethyl, right? So we got 2, 2, 6, trimethyl heptane. Okay, there we go. All right, on to our last problem here. Okay, let's find the longest chain. This looks like it's gonna be our longest chain, right? Okay, so again, we count from left and then count from the right and compare. 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8. Okay, so our first branch point, if we count using blue, the first branch point would be on carbon 5. Okay, would be on carbon 5. If we count following green, the first branch point would be on carbon 4. So we're following the green counting here. So I'll erase everything and leave the green counting system, I would call it. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, meaning we have octane, right? For 8 octane. Okay, so our first branch point here, in fact, our only branch point, we got two things attached to it. One is a methyl group. So we got 4-methyl. And the other one is an ethyl group. Okay, so we got 4-ethyl. Okay, so at this point, we could combine all the information we have. Okay, so we got ethyl and we got methyl, and E comes before M in the alphabet. So we got 4-ethyl, 4-methyl octane. Okay, so alright, so finally we have named all the molecules we have for problem number 50. Alright, moving on to problem 51. Okay, we're still on IUPAC naming, and this time we are naming isooctane. Okay, so we are getting the IUPAC naming for isooctane. This is the common name for it. Okay, so first step, let's find the longest chain, and I think it's easier with the condensed structure right here to see that this is the longest chain that we have. Okay, so I'm going to number from the left and then from the right, and let's see where we hit our first branch point. We got 1, 2, 3, 4, 5, and then from the right we got 1, 2, 3, 4, and 5. Okay, so it looks like either way we're gonna hit our first branch point on carbon number 2. Okay, but as you see, if we follow the green numbering, if we count from the left, once we hit carbon 2, we have 2 groups attached to it. Okay, as compared to when we count from the right side, when we hit our first branch point, we only have 1 group attached to it. So this counting from the left side would be our priority. Okay, and I'll explain a little bit more of that as we go. Alright, so we're counting from the right, as I mentioned, and I want to deal with this using our molecular model, since it has more space and it's easier to just write. Okay, so we got 5 carbons in our main chain, which means we have a pentane. Okay, we have a pentane. So on carbon 2 right here, we have 2 CH3 groups. Alright, so that's a methyl group. So we have 2-methyl and another 2-methyl. I'm just going to separate them for now, and we'll combine them later. Okay, and then we have carbon 4 here with another methyl group. So we have 4-methyl. Alright, so at this point, we've gone over all our branch points, and we could combine the information we have. So we have 3 methyls, which gives us trimethyl. Okay, and then we're just listing the numbers in order. So we have 2, 2, 4, trimethyl pentane. Okay, if we have counted from the right side and following this orange numbering right here, we're gonna have 2, 4, 4 trimethylpentane, and as you could see, this would give us a lower total number, so that's why we counted it that way. Okay, but anywho, this is our IUPAC name for isooctane.
Alright, so problem 52, we are writing condensed structures. Okay, so let's just go for it. Part A. Okay, part A says we have 3-ethylhexane. So hexane means we have six carbons in our molecule, right? So 1, 2, 3, 4, 5, 6. Okay, and then 3-ethyl here means we got an ethyl group on our third carbon. So this would be my third carbon, and I'll go ahead and add CH2, CH3. So that's your ethyl group, okay? And all that's left to do here is to add those hydrogens, okay? So our first carbon here on the left could handle 3 more hydrogens, okay? And then the second one could handle CH2. And this third carbon currently has 3 carbons bonded to it, so it can only make 1 more bond with hydrogen, okay? And then this fourth carbon could handle 2 more, as well as this carbon, and the last carbon only has one carbon connected to it, so it could make 3 more bonds with hydrogen atoms, okay? So that should be part A. Part B, okay, we got 2,2,3 trimethylpentane, okay, pentane. So pentane means we got 5 carbons. So I'll go ahead and write 5 carbons here for 5, okay. 2,2,3 trimethyl means we got 3 methyl groups, and they're on carbons 2, 2, and 3. So carbon 2 has 2 methyl groups, and carbon 3 has 1, okay. So I'll go ahead and fill those bonds with methyl groups, okay, CH3, and another CH3, okay. So now that we have all our groups connected, all we have to do is fill up the carbons with hydrogens, okay. So this first carbon would be CH3, right? The second carbon already has 4 carbons connected to it, so it can't handle another bond, so we could leave it alone, right? This third carbon right here has 3 carbons connected to it, so it could handle 1 more hydrogen, okay? And this fourth carbon could connect or could bond with 2 hydrogens more, and our last carbon can be CH3, okay? So that's it for our part B, okay? So just as a reminder for everyone that these spaces are not supposed to be part of our condensed structures. That's just an extra space that was left after my work, but when you write your structures, please make sure you don't have those spaces, okay? So part C, we got 3-ethyl 3,4-dimethyl heptane, okay? So whenever I try to read these structures, I kind of start ignoring the groups first, and then I focus on the first thing that I need to know, which is how many carbons are there, okay? So now I know there's 7, so I'll go ahead and write 7. 1, 2, 3, 4, 5, 6, 7, okay? Now I got 7. Now I worry about the groups, right? So I got 3-ethyl. So I'll go to the third carbon and add an ethyl group, okay? So I'll put it up here. Ethyl would be CH2, CH3, okay? 2 carbons. And then I have 3,4-dimethyl. So I got two methyl groups. One would be on carbon 3 and one would be on carbon 4. So CH3 here and CH3. So 3,4 dimethyl. Okay. So now that we have all our alkyl groups connected, we fill those bonds with hydrogen atoms. Okay. So what I mean by that is that carbon needs to have four bonds around it, and we fill those bonds with hydrogen if they're missing some. Okay. For example, this first carbon here, this first carbon has one carbon connected to it, so that means it needs 3 more bonds, and that's going to be filled up by hydrogen. Okay. So the second carbon would be CH2. This third carbon already has 4 carbons connected to it, so it doesn't need any more bonds with hydrogen. Okay. Fourth carbon here could handle 1 more hydrogen. Okay. These next 2 carbons could handle 2 hydrogens each, and our last carbon here would have 3 hydrogens connected to it. Okay. So that should be our structure for part C. And finally, we have structure part D. Okay. We got 5 isopropyl 2-methyl octane. So again, as you notice, I just kind of ignored all the groups there and went to the part where it says octane. Okay, so that means I have 8 carbons. So let's go ahead and draw 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then I have an isopropyl group on carbon 5. Okay, so 1, 2, 3, 4, 5. This is carbon 5. And I have an isopropyl group. So hopefully you remember what isopropyl looks like. Okay, so this is what it looks like. It has a carbon that splits and connects to two more methyl groups. Okay, and finally I have the 2-methyl right here, so I'll go to carbon 2 and add a methyl group. Okay, all that's left for us here is to make sure that every carbon is connected to 4 things. If it's not, then fill it up with hydrogen. Okay, so first carbon here needs 3 more bonds, so we're filling that out with 3 hydrogens. Okay, second carbon could handle 1, then we have CH2 for the next 2 carbons. Okay, this 5th carbon has 3 things connected to it, 1 on the left, 1 on the right, and 1 below. Okay, so that means it could handle 1 more hydrogen. Then we have CH2 for the next 2, and our last carbon here would have 3 hydrogens connected to it. So there you have it. That's all our structures for this problem. Alright, problem 53. We are drawing structures, and as you would probably notice by now, they're all cyclic structures. Okay, and the reason that I have these cyclic structures pre-drawn below is because I'm not very good at drawing polygons, so hopefully you are. But there you have it. I have our cyclic structures pre-drawn, so let's just go for it. Right, starting with part A here. Part A says cyclooctane. Okay, so that just means cyclo meaning you have a ring, and octane that means you have 8 carbons. Okay, so 8 carbons in a ring would give you an octagon, right? So outside of chemical or chemistry context, that's called an octagon. So you're just gonna have to draw an octagon. Okay, which is what I have here in part A. So I have a cyclic structure with 1, 2, 3, 4, 5, 6, 7, 8 carbons in it. Okay, so that's pretty much it for part A. Part B is a little more complicated. We have function groups now attached to it, right? We got 1,1-dimethyl cyclopentane. Okay, so pentane means we have 5 carbons, and cyclo means they are in a ring. Hence this pentagon that I have right here on the right side. Okay, and then we have 1,1-dimethyl. Okay, 1,1-dimethyl means we have two methyl groups and both of them are on carbon 1. Okay, so at this point you're assigning numbers to carbons and it's arbitrary, right? So you could use any of these carbons as your carbon 1. So I'll just choose this carbon right here. Okay, so I'll choose that, and there are two methyl groups attached to this carbon, so I'll go ahead and add those methyl groups. So there you go, that's 1,1-dimethyl cyclopentane. So this is part B. Okay, so moving on to part C here, we got 1, 2, 3, 4 tetramethyl cyclobutane. Okay, cyclo meaning you have a ring, and butane means you have 4 carbons in your ring. So it's kind of like a square, right? So so first is you draw that square or diamond, whatever you want to call it, and which we have right here. And we have 1, 2, 3, 4 tetramethyl. Okay, so that means we have 4 methyl groups, tetramethyl, and they're on carbons 1, 2, 3, and 4. Okay, so each carbon here is gonna have a methyl group. So for this example, doesn't matter how you count it because they're all gonna have the same methyl group, right? So you can choose which of these carbons would be your carbon 1, which would be 2, 3, and 4. In this case, it doesn't matter. Okay, so there you go, we have 1, 2, 3, 4 tetramethyl cyclobutane. So that is part C. Finally here we have part D, and we got 4-ethyl 1,1-dimethyl cyclohexane. Okay, so whenever we are drawing structures, I think it's very important to start with the base structure, which is cyclohexane here. So as you noticed, I kind of just skipped over all the groups, all the function groups, and I'll just pay attention to those later. So this is part D. So we have a cyclohexane, which is outside of chemistry concept, that would be called a hexagon. Okay, so you got six carbons in one ring, cyclohexane, and then we got 4-ethyl 1,1-dimethyl. So I want to go ahead and just number my carbons here, and again, doesn't matter which one is carbon 1, so I'll just choose that to be carbon 1, 4, 5, 6. Okay, so now that they're numbered, I can go ahead and put my groups. I have 4-ethyl, so I'll go to carbon 4 here and add an ethyl group. So I'll have CH2, CH3. Okay, so that's ethyl. And I have 1,1-dimethyl, meaning I have 2 methyl groups and both of them are on carbon 1. So this is methyl group and another methyl group. So there you have it. Those are all our structures for problem 53. Alright, problem 54 is asking us about aromatic compounds, and why is it that when a compound is aromatic, why is it that it doesn't necessarily mean that it smells nice? Okay, so why is that the case? Well, that's because the term aromatic refers to a class of compounds that is made of a 6-membered ring that has 3 double bonds. Okay, so this is what the term aromatic means. It does not mean it has anything to do with the smell. Okay, so it is made for these types of compounds. Okay, so hopefully that clarified that term.
An addition reaction is an organic reaction in which a reagent adds to the multiple bond of the unsaturated reactant to yield a saturated product.
Okay, problem 56. We are writing structural formulas for these molecules that they described for us. Okay, so there's a lot of different answers for these kind of problems, so I'm going to come up with one, but if it's not the same as the one you came up with, it doesn't mean it's wrong. Okay, so these descriptions have many other isomers that could come with it, so I'll just write what I have in mind and we'll go from there. Okay, so starting with part A. Part A says we want an alkene with 5 carbons. Alkene with 5 carbons. Okay, so that's exactly what I'm gonna do here for part A. I will write my 5 carbons. Okay, 1, 2, 3, 4, 5. Okay, and I want a double bond somewhere, and I don't know, I just want to put it here on the very first carbon. Okay, so now that we have that, I actually need to rewrite that. Now that we have this double bond on the first carbon, right, we could fill up the rest of the bonds with hydrogens. Okay, so this bond would have CH2, right, could handle 4 bonds, and the same, oh, not the same, the second carbon could only handle 1 hydrogen because it has 3 bonds before that. Okay, so then we have CH2, CH2, and CH3. Okay, so that's the structure that I came up with for part B, and again, that double bond could be anywhere else in this structure, so that's just where I wanted to put it. Part B. Okay, part B, we got an alkyne with 4 carbons, so I want to start with having 4 carbons, right? 1, 2, 3, 4. Okay, so I have 4 carbons, and we have an alkyne. We have an alkyne, meaning we have 3 bonds, or a triple bond. We have a triple bond somewhere, and I'm just deciding to put that again on the first carbon. Okay, so now that we have that triple bond, let's go ahead and fill it out with hydrogens, right? This first carbon can handle 1 more hydrogen, plus those 3 bonds gives it a total of 4 bonds. This second carbon is saturated with 4 bonds, so we could leave it alone. So I'll just write the next carbon right next to it, right? And then we have this carbon, which could handle 2 more hydrogens, and finally we have CH3 at the end. Okay, so that's what I came up with part B. Again, if yours doesn't look like this, it doesn't mean it's wrong. Okay, so there should be isomers that are possible for this molecule. Okay, part C. Part C, we got a substituted aromatic compound with 8 carbons. Okay, so, well, I know one very, very common aromatic compound, right? I have benzene, right? So what I want to do here is just to draw that benzene. Okay, draw that benzene. Okay, so it says that we need 8 carbons total, and benzene has 6, right? Benzene has 6 carbons. So we need 8 total. So 8 minus 6, meaning we need 2 more. 2 more carbons in this molecule. And it also says substituted aromatic compound, meaning it does have alkyl or functional groups that come with it. So I need 2 more carbons, and well, I'll just add 1 ethyl group, right? Ethyl group has 2 carbons. So CH2, CH3. So there you go. Is my aromatic compound substituted? Yes, it does have this alkyl group. Okay, does it have 8 carbons total? Yes. I have 6 from the aromatic ring, and then I have 2 from the ethyl group. So it satisfies all the requirements for part C. Again, all of these structures are just what I came up with. They do have isomers that are also correct. Okay.
There are 3 dienes with the formula C3H8, and these are, so diene is a compound with 2 double bonds. CH3, so 1, CH3, CH, double bond CH, CH, double bond CH2. So there's, sorry, this is C5H8, not C3H8. Let's fix that. C5H8, dienes with C5H8. Second diene will be CH2, double bond CH, CH2, CH, double bond CH2. So there's the second diene. And the third diene is going to be CH2, double bond CH, C, double bond CH2, and a methyl substituent here. So those would be the 3 dienes that can be formed from C5H8.
Problem 58, we're still on IUPAC naming. Okay, so let's go and start with part A. As usual, let's go and find the longest chain we could find, and I think for this one it's pretty obvious. All right, and here we have a double bond, right? And the rule is whenever we have a double bond or a triple bond, we count from the side where we're closer to that bond. Okay, so what I mean by that is this double bond right here looks like it's closer to the right side. And I mean, you don't really have to estimate. You could check, but I think it's pretty clear to see that there's only 2 carbons on the right side of the bond and there's 3 on the left. So it's closer to the right side. So we count starting on the right side. So let's go and count. We got 1, 2, 3, 4, 5 on our main chain. Okay, so let me give a space for part A down here. Okay, so we got 5, meaning we have a pentene. Right, so pent for 5 and pentene because we have a double bond. Okay, and that double bond starts on carbon 2, right? Starts on carbon 2. So this would actually be 2-pentene. Okay, just kind of ran out of space there. But okay, so we have 2-pentene. Next is we check our branch points. And we see here on carbon 4 that we have a methyl group branching out. So we have a 4-methyl. Okay. So now that we have all the information we need, we could combine all of it and come up with our answer. Okay, so we have only one group that we need to take care of. So we got 4-methyl, 2-pentene. Okay, so that should be our answer for part A. Let's go to part B now. Okay, so part B. Alright, so again, as usual, let's find the longest chain, and this looks like our longest chain right here, right? We got 2 carbons up here compared to just 1 if we go along a straight line, okay? And again, we count from where our double bond is closer, and for this one, it's pretty obvious that it's on the right side. Okay, in fact, it's at the end of the right side here, okay? So we're counting from the right side here, 1, 2, 3, 4, 5, okay? So just like part A, we got pentene, but this time our double bond starts on carbon 1, right? So we have 1 pentene, because there's 5 carbons, and pentene, E because we have a double bond, okay? So next is we take care of our branch points, and for this one, we actually only have 1. We have a methyl group connected to carbon 3, okay? So we have, let me use a different color pen here, okay? We have 3-methyl, okay? So I think that's all the information we need, and we could proceed to combining all these information. Okay, so we have 3-methyl. We name our branching group first. So 3-methyl, 1-pentene. And that's our answer for part B. Okay, so part C now. We have a benzene ring, and connected to our benzene ring are 2 chlorine atoms, okay? So we gotta count 1 on the carbon where our functional group is, or our atom is, so this would be 1, and we gotta count 2 on the closest branching group as well, so this has to be 2, okay? Because if we count 2 here, then this chlorine would be carbon 6, and we don't want that, so this chlorine would be on carbon 2, okay? So we have dichloro, right? So we have 1, 2, 1, 2, since that's where we have our chlorine atoms, and we got dichloro for having 2 chlorine atoms, right? Dichloro, benzene. Okay, alternatively, the way that they are positioned, since they are next to each other, we could also name that ortho. Okay, so we write O for ortho. O, dichlorobenzene. Okay, so there's two possible IUPAC names for part C. Alright, moving on to part D. Part D, as usual, let's find the longest chain. And I think for this one, it looks like it doesn't matter, right? So even if you get this methyl or this methyl, it's going to be the same length, since it's just 1 methyl for both choices. Okay, so let's just take the straight chain. I think it's simpler. And let's count and see where we hit our double bond first. Okay, so if you count from the left, we got 1, 2, 3, 4. And if we count from the right, we have 1, 2, 3, 4. Okay, so either way, looks like either way, I know it's kind of getting messy here, but either way our double bond is gonna hit carbon 2 first. Okay, but if we count from the right and follow the green numbering, once we hit carbon 2, not only do we hit our double bond, we also hit this branch point right here. Okay, so kind of shooting two birds in one stone right there. So we are gonna count from the right on this one. So let's count from the right. We got 1, 2, 3, 4, and since we have 4, that's a butene because of the double bond, and it starts on carbon 2, right? Double bond starts on carbon number 2, and that gives us 2 butene. Okay, and I didn't write that well, but you get what I mean. That's 2 butene, and we have this methyl group sticking out from carbon 2 as well, so we have a 2 methyl. So combining all those information, we have 2 methyl, 2 methyl, 2 butene. Okay, and that would be our answer for part D. Alright, finally we are on part E here. Okay, and again, find the longest chain, and it looks like it's pretty obvious. This whole thing here is our longest chain. So again, we are counting from where our triple bond is closest. Okay, so this applies to both double and triple bonds. So it's closer to the left, so we're counting from the left first. 1, 2, 3, 4, 5. Let me rewrite that. 5, 6, 7, and 8. So we get 8. And our triple bond starts on carbon 3. So we got 3 oct. Rewrite that. Got oct for 8, and YNE because of the triple bond. So we got a 3 octane. Okay. And last thing that we need to do here is to account for our methyl group sticking out from carbon 7. Okay. So we got a 7 methyl group. Okay. Alright, so time to combine all the information that we have. We got 7 methyl, 3 octane. Okay, so that's our answer for part E, and finally we're done here. We have named all the molecules we have for problem 58. Okay, so we're drawing structures for problem 59. So let's just go for it, starting with part A. We got cis-2-hexene. So hexene meaning we have 6 carbons, and 2 and ENE means we have our double bond on carbon 2. Okay, so I actually want to start drawing this with carbon 2 having the double bond with carbon 3, right? And it says cis, meaning our hydrogens would be on the same side, or our carbons connected to carbons 3 and 4, or 2 and 3, sorry. This would be carbon 2, and this would be carbon 3. Okay, so cis, meaning our carbons connected to it would be on the same side, as well as our hydrogens, right? So if this is carbon 2, meaning we're going to have carbon 1 connected to it. Okay, so this is carbon 1. And then we're going to have that carbon 4 connected to it as well. Okay, so that's what we mean by cis, they're going to be on the same side, and the same is true for the hydrogens. Okay, so this carbon is going to have hydrogen, this is going to have a hydrogen, and they're going to be on the same side. Okay, so carbon 1 would have 3 hydrogens connected to it, that because we've pretty much gone over the important part on this molecule. So everything that we're going to do here is just filling up those carbons and hydrogens that we have left. Okay. All right, so we got carbon 4, and this is most likely going to be CH2, right? And then we got carbon 5, and finally we have carbon 6, which will be a CH3. Okay, so there we go. That's our cis-2-hexene. Moving on to part B. We got 2-methyl-3-hexene. Okay, so as usual, we got a 6-carbon molecule with a double bond on the 3rd carbon. So again, I want to draw that starting with carbon 3, right? Starting with carbon 3, then we have it double bonded to carbon 4. So this is carbon 3, this is carbon 4, and it doesn't tell us about it being cis or trans, so we don't really have to show it, just like how we showed part A. So as long as we know that carbon 3 would be a CH, right, and carbon 4 would also be a CH, okay, and that would be connected to CH2 being carbon 2 and a CH3 for carbon 1. Okay, so this is carbon 1, carbon 2, 3, 4, and then actually we'll edit that a little bit later, but let's go forward with carbon 5 and 6 for now. So we'll have, don't need that bond, we'll have CH2 for carbon 5 and CH3 for carbon 6. Okay, so we got 5, 6, and now we take care of that 2-methyl right there. So on carbon 2 we have a methyl group sticking out, so let me erase this number 2 right here, and we have a methyl group sticking out, which means we're gonna have to reduce the number of hydrogens that we have. Okay, so instead of CH2 we're only gonna have CH. Okay, so that should be our structure for part B. So next, and finally, we got part C, right? We got 2-methyl-1,3-butadiene. Okay, so that's a pretty long name. This but tells us we have 4 carbons, right? So I want to go ahead and write 4 carbons here. We got 1, 2, 3, 4. Okay, 1, 3 tells us we have the double bonds on carbon 1 and then another one on carbon 3. Okay, so we have 2 double bonds on this molecule. That's also why we have this diene in our naming. So carbon 1 would have a double bond with carbon 2, and then carbon 3 is going to have a double bond with carbon 4. Okay, all right, now that we got that, all we have to do is take care of the 2-methyl group. Okay, so carbon 2 would have a methyl group with it, and after that we could go ahead and fill out the missing hydrogens. Okay, so the first carbon would have 2 hydrogens. Okay, and carbon number 2 here already has 4 bonds, so it's good to go. Our carbon 3 is missing a hydrogen to make it 4 bonds, and this last carbon here needs 2 hydrogens. Okay, so That should be our answer for part C. Alright, so finally, we have the structures for all our molecules here. Alright, so for problem 33, we have this molecular model, and we're asked to provide a condensed structure, okay? So before we start, I want to remind everyone with what the specific spheres mean. So whenever we see a black sphere, that represents a carbon atom. Whenever we see a white sphere, that represents a hydrogen atom. And the red sphere represents oxygen, okay? And also I want to go ahead and number our carbons. That makes it easier for us to talk about it, right? So let's go ahead and count carbons. 1, 2, 3, 4, 5, 6, and I'll call this carbon down here 7, okay? So let's go for it and start. So carbon 1, we see that it has 2 hydrogens attached to it, right? There's 2 white spheres. So let's go ahead and write CH2. And we see that it is double bonded to carbon 2. So let's go represent that double bond. And then carbon 2 doesn't really have any hydrogens attached to it. So we're writing just C for now, okay? So it is connected to carbon 3 with 2 hydrogen atoms right here. So let's write CH2, right? I'll just go ahead and rewrite. I feel like I'm not writing it well. So CH2, okay. And then we also see that carbon 2 is connected to carbon 7, right? This is carbon 2. Oops. This is carbon 2 right here, and it is connected to carbon 7. And carbon 7 has 3 hydrogens in it. 1, 2, 3, right? So we'll have a bond here on carbon 2, and we'll have a CH3 attached to it. So this CH3 would be our carbon 7. Okay, excuse me. Proceeding to carbon 4. Carbon 4 also has 2 hydrogen atoms, so we're writing CH2. Carbon 5 has 1 hydrogen atom attached to it, right? So for now we're just writing CH, just 1 hydrogen atom. And then it has this functional group connected to it, and as mentioned, this red sphere is an O, and this white sphere is an H. So we have an alcohol group coming out of it. So let's go ahead and add that to our structure. So I'll just put it down here, and it is connected to an OH, right? Doesn't really matter if you put it below the C or above. At least for condensed structures, it doesn't really matter. And finally, we have carbon number 6. Carbon number 6 here has 1, 2, 3 hydrogen atoms. So we have CH3 at the end of our structure. And we're pretty much done here. This is the condensed structure of the given molecular model. Okay, so problem 60. We have 3 molecules here, and we're asked which of these is capable of cis-trans isomerism. Okay, so we got 1 hexene, 2 hexene, and 3 hexene. And I do have those molecules pre-drawn in here just so we could talk about it easier, okay? So, starting with 1 hexene, we have this double bond between carbon 1 and 2, hence the name 1 hexene. And the way that this structure is drawn, it doesn't show you the hydrogens, right? So I want to go ahead and draw that just so it's easier for us to see. And before I draw the hydrogens, I want to remind that there's a carbon in here and a carbon right there. Okay, so go ahead and draw the hydrogens. Okay, so there's 2 hydrogens in there, and then that carbon is double bonded to carbon 2. Okay, so carbon 2 has 1 hydrogen, right? So it could only handle 1 more hydrogen. So now we can analyze this molecule if it's capable of cis-trans isomerism. And as you can see, carbon 1 is connected to 2 hydrogens. It's connected to 2 hydrogens, and carbon 2 is connected to 1 carbon. Okay, so 1 hexene is not capable of cis-trans isomerism because there is no carbon connected to carbon 1 here. Okay, so the answer for A is no, it's not capable of cis-trans isomerism. Okay, so proceeding to 2 hexene here. Okay, again, I want to go ahead and draw those hydrogens along the double bond. Right, so we got 1 hydrogen here on carbon 2, and we have 1 hydrogen here on carbon 3. Okay, and then as you can see, you have carbon 4 right here and carbon 1 right here, and they are on opposite sides of the double bond. Okay, right there on opposite side. This one's, if you could think about it, this carbon 4 is kind of going up the double bond, and carbon 1 is kind of going down. Now, is there another way to draw this? Well, I think there is, right? We could draw one of this carbon 1 right here going up like that, right? So, and this is what that is gonna look like. Okay, so if we draw carbon 1 going up, this is what it's gonna look like. Okay, so in this molecule, both the carbons connected to carbon 2 and 3, so we got 1 and 4. Carbons 1 and 4 are on the same side of the double bond, right? They're kind of on the same side. They're both going up. So this would be your cis for same side. Okay, cis isomer and trans isomer. Sorry about that. Okay, so well then, yes, 2 hexenes capable of cis-trans isomerism. There's 2 ways to draw those bonds around the double bond. Okay. Next is 3 hexene right here. So we have carbon 3 and 4, hence the name 3 hexene. Okay. And as you can see, carbon 2 right here is kind of going up the double bond if you think about it, and carbon 5 is going down. Okay. So since they're going on opposite directions, that can be our trans isomer. Now, this can only be trans isomer if we could prove that we can draw this any other way. Okay, and the other way that we could try to draw is to draw these carbons going on the same direction, and this is what it's gonna look like. Okay, so here we still have that carbon 3 and 4, and they're double bonded to each other, and then we have 2 and 5 right here, both going on the same direction. Okay, so they're on the same direction, so that would be our cis isomer. Okay, so as you can see, we only have 2 hexene and 3 hexene that's capable of cis-trans isomerism. Therefore, our answer would be B and C. Okay, so I need to box that, I think. So B and C are capable of cis-trans isomerism.
So we're asked which of the following can exist as cis-trans isomers. A can exist as cis-trans isomers. So the cis configuration for A will be with the 2 hydrogens on the same side, CH3, and this would be CH, CH3, and CH3C. So there's the cis configuration for A. The trans configuration for A will be this configuration here where the hydrogens are opposite, and we will get this configuration here for the trans. So A can exist as cis-trans isomers. B cannot exhibit cis-trans isomerism. So there cannot be, so as the CH2 group on the right end has 2 hydrogens attached, so we can't have different groups there. C does exhibit cis-trans isomerism. So for C, the cis isomer will be this configuration here. Chlorine there, and then the trans isomer we can draw as this isomer here, and so this one does exhibit cis-trans isomerism. So A and C are able to show cis-trans isomerism, while B for A, let's write the reaction of 2,3-dimethyl-2-butene. So 2,3-dimethyl-2-butene. And it's going to be reacted with H2 in the presence of a palladium catalyst, and this would yield CH3 CH3, and we would get CH3 CH3 H and H. For B, again 2,3-dimethyl-2-butene. And this would be reacting with bromine, Br2, and this would yield CH3C CH3, and this would be H. Oh no, not H and H. These would be Br, CH3, and CH3. And for C, 2,3-dimethyl-2-butene. And this is going to react with H2O with a H2SO4 catalyst, so the presence of acid, and this would yield CH3C CCH3. This would be CH3 CH3 OH and H. So there are our completed reactions. Let's complete the following reactions of paradichlorobenzene. For A, we have a halogenation, so paradichlorobenzene. is going to react with bromine in the presence of FeBr 3, and this will yield the bromine group being attached here. So there's the halogenation. For 2, we're going to show a reaction of paradichlorobenzene with HNO3. And we're using H2SO4 as our catalyst. And this is a nitration. So this will yield this molecule here, Cl, Cl, and NO2. And for C, we have paradichlorobenzene, and it's going to react with Cl2 in the presence of FeCl3 as a catalyst. This is another halogenation, which will yield Cl, Cl, and Cl.
Okay, so problem 64, we are drawing structures. Okay, so let's go for it, starting with part A. Part A here we have 2,4-dimethyl-2-pentanol. Okay, so we have that pent right there, meaning we have 5 carbons. So I want to start with drawing 5 carbons here. 1, 2, 3, 4, 5. Okay, and then next we got this suffix "ol", meaning we have an alcohol, and that alcohol group is on carbon 2. Okay, hence 2-pentanol. So let's go ahead and put that alcohol group on carbon 2, right? So there you go. Next, we got 2,4-dimethyl. Okay, we got 2,4-dimethyl, meaning we have methyl groups on carbon 2 right here, and carbon 4. Okay, now this methyl group could be below carbon 4, but I just chose to put it above it. Okay, so now we have all our functional groups, and all that's left for us to do is fill it out with hydrogens. Okay, so carbon 1 here is only connected to carbon 2, so it can handle 3 more hydrogens, so it's going to be ACH3. Okay, carbon 2 already has 4 things connected to it. It has this carbon, and then carbon 3, and then 2 more groups right here. Okay, so it can't handle any more hydrogens. Carbon 3 right here has 2 other carbons connected to it, so it can handle 2 more hydrogens, right? And then carbon 4 has 3 things connected to it, so it can handle 1 more. Okay, it can handle 1 more hydrogen. And then finally our carbon number 5 here could handle 3 more. Okay, so really the key here is to make sure every carbon is connected to 4 things. If not, then fill it out with hydrogen. Okay, so moving on to part B. Okay, part B, we got 2,2-dimethyl cyclohexanol. Okay, so that cyclohexanol means we have this 6-membered ring right here, and we're gonna use that. Okay, so cyclohexanol, meaning we have the cyclohexene, and then it has an alcohol group. Okay, so let's go ahead and add that alcohol group. Just want to add this here on top. Okay, so whenever you have a cyclohexanol or whatever functional group your ring has, that carbon would be your carbon number 1. Okay, that will always be your carbon number 1. So let's go ahead and count our carbons here. 1, 2, 3, 4, 5, 6. Okay, and then next we got 2,2-dimethyl. Okay, so meaning we have 2 methyl groups on carbon 2, right? So this would be our carbon 2, and we just have 2 CH3 groups in there. Okay, CH3, CH3. Okay, and that's pretty much it for part B. Okay, again, the key here is setting this carbon as carbon 1. Okay, next is part C. Okay, part C, we got 5,5-diethyl 1-heptanol. Okay, heptanol right here tells us that we have 7 carbons. So let's go ahead and start with 7 carbons. 1, 2, 3, 4, 5, 6, 7. Okay, and then we got 1 heptanol, meaning we got the alcohol group on carbon 1. So let's go ahead and add that. And finally we got 5,5-diethyl. So diethyl meaning we have 2 ethyl groups and they're both on carbon 5. So this is carbon 5 right here, and we are going to have 2 ethyl groups. So CH2, CH3. That's 1 ethyl group, and then another one up here. Okay, so now we have all the groups that we need. All that's left is to fill out with hydrogens. Okay, carbon 1 has 2 things connected to it right now. It has the alcohol group and this carbon, right? So let's go ahead and fill it out with 2 more hydrogens. Okay, carbon 2 can be CH2. Same is true for carbon 3. Carbon 4 as well. Okay, so for carbon 5, it doesn't really have any more spots. It's currently connected to 4 things already, so we'll leave it alone. We got CH2 for carbon 6, and finally carbon 7 could handle 3 more hydrogens. Okay, so obviously we have the space here. That's just extra space. If you rewrite your molecule, you're not supposed to have any space there, but that's what we have for part C. Finally, we got part D, right? We got 3-ethyl 3-hexanol. Okay, so we got 6 carbons from hex right here. So I'm gonna go and draw 6 carbons here. 1, 2, 3, 4, 5, 6, and it says 3-hexanol. So carbon 3 has an alcohol group, right? And we got 3-ethyl. Okay, let me change the color for that. Let's use pink. So 3-ethyl, meaning carbon 3 also has an ethyl group. So CH2, CH3. Okay, so that's pretty much it for part D. All that's left for us to do is fill out with hydrogens. Okay, so first carbon would have 3 hydrogens. Got CH2 in here. Carbon 3 has 4 things connected to it right now. Okay, got 1, 2, and then it's connected to this carbon and that carbon as well, so we can leave it alone. Okay, and then we got carbon 4, can handle 2 more hydrogens, carbon 5 as well, and finally carbon 6 right here would have 3 hydrogens. Okay, then again, as I've mentioned, we don't really have this space right here. That's just extra space from that we have. Okay, so when you rewrite this molecule, it's not supposed to have that space right there, but that's all our structures. Okay, so problem 65, we're still drawing structures here and we're dealing with amines. Okay, so I'm starting with part A. We got propylamine. Okay, propylamine, and the way I want to start doing this is to start with the amine backbone. Okay, so What I mean by that is we just have this basic structure of an amine. So we have a nitrogen with 3 bonds to it. And part A says we have a propyl group attached to this amine. So propyl meaning we just have 3 carbons, right? We got CH2, CH2, CH3, okay? So that's our propyl group. And of course, we got 2 more bonds here which would be connected to hydrogens, okay? So that should be propylamine for us. Moving on for part B here, we have diethylamine, okay? So I realize I have this cyclohexane in the wrong spot here. Okay, so part B, we got diethylamine. So again, I want to start with kind of the basic structure for an amine, right? So just a nitrogen connected to 3 things. So it says diethyl, meaning we have 2 ethyl groups attached to nitrogen, okay? So we have one ethyl group right here, CH2, CH3, and another one right here. So it doesn't really matter where you put it, right? And of course that last bond would be connected to hydrogen, okay? So that should be our diethylamine. Part C is a cyclohexylamine, okay? Cyclohexylamine. Okay, so that's why I have this cyclohexane right here, and it's going to be connected to one of the bonds with nitrogen, okay? So since I already have this cyclohexane right here, I just want to connect that to nitrogen, right? And of course nitrogen is going to have 2 more bonds, and those bonds would be filled up with hydrogen, okay? So that should be cyclohexylamine for us, and I think we all have our structures here. Problem 66 is asking for us to compare aldehyde versus ketone, okay? So before we start comparing, I want to go ahead and draw what we have. So an aldehyde would be a carbon connected to an oxygen via a double bond and a hydrogen, and it's going to be connected to another carbon right here, okay? So this could be anything. So that would be aldehyde. Okay, ketone would have a carbon and then another carbon and another carbon, and this middle carbon would be double bonded to oxygen, okay? And this carbons at the end could be connected to anything, okay? So that should be our ketone. So I think the difference is pretty clear here, okay? For it to be a ketone, it has to be somewhere in the middle of the molecule, right? So it has to be in the middle of 2 carbons, hence it will be somewhere in the middle of your molecule, okay? And for aldehyde, for it to be an aldehyde, it kind of has to be at the end, right? Because this is hydrogen right here, and it's not going to be connected to anything else. So for it to be an aldehyde, it has to be a terminal group, okay? So I guess the biggest difference between aldehyde and ketone is that aldehyde would be a terminal functional group, meaning it's always at the end, and ketone would always be in the middle, okay?
Carboxylic acids, esters, and amides all undergo carbonyl group substitution reactions.
problem 68, we are identifying the carbonyl groups on all of these structures that are given. Okay, so starting with part A, I think part A is pretty clear right here. Okay, so what we just have a ketone right here. Right. So part A would just be a ketone. Okay. Part B right here may be a little bit tricky. First of all, it's terminal, meaning it's connected to the very end carbon. Okay, so we have two choices here. It could either be an alcohol, or an aldehyde. Okay, and so the safest way here is to just count how many things are attached to carbon. Okay, so we got 1. This is attached to our carbon, and then we have 1 hydrogen, right? So it has 2 things attached to it. So that oxygen has to be double bonded to carbon in order to fill those 4 bonds to carbon, right? So that means since we have a double bond, that means we have an aldehyde. Okay, and another easier way or faster way to identify if it's an alcohol or an aldehyde is that an alcohol would always be written as OH, right? And aldehyde would always be HO, okay, or CHO. Okay, so if it's OH, it's definitely alcohol. If it's written as CHO, then it's aldehyde. Okay. Part C. So here's our oxygen right here. And again, this question stem already tells us we have a carbonyl group, but if it doesn't tell you that, this oxygen could either be an ether, or because it's somewhere in the middle of the molecule, it could be a ketone. Okay. So as discussed in a previous problem, if a carbonyl group is somewhere in the middle of a molecule, then it is a ketone. So part C here would be a ketone, okay? Since we know it is a carbonyl group. If you want to make sure it's not an ether, then you can go ahead and count the bonds connected to carbon, and you'll see that it needs to be double bonded to oxygen. Okay. Part D. Part D is right here. And I think it's pretty clear. We know that this is a carbonyl group, right? So it's going to be a C double bonded to oxygen. And we have that nitrogen in there. So that makes this group our amide. Okay. Okay, on to our last part, part D. We got 2 oxygens, okay? So we really only know 2 functional groups with 2 oxygens in it. One would be a carboxylic acid. That's a hydrogen. We rewrite it. Carboxylic acid, or an ester. Right? The only difference would be either you have a hydrogen connected to your oxygen or another carbon. Okay. In this case, as we see, we have this carbon connected to our oxygen, right? Meaning our functional group here would be ester. Okay.
For A, we are to draw 3 amides with the formula C5H10NO. So one amide could be CH3, CH2, CH2, CH2C double bond ONH2. So there's one possibility. Second amide is CH3, CH2, CH2, C double bond O, NH, and the CH3 group here. And a third amide could be CH3, CH2C, double bond O, and CH3, CH3. So there's 3 amides with the formula C5H10NO. And for B, we're going to draw 3 esters, and these esters are going to have the formula C6H12O2. So one ester is going to be CH3, CH2, 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 C double bond O, OCH3. So there's one possibility. A second ester can be CH3, CH2, CH2, C double bond O, OCH2, CH3, and a third ester can be CH3, CH2, C double bond O, OCH2, CH2, CH3. So there are 3 esters with the formula C6H12O2.
Alright, so problem number 34 is asking us to identify the functional groups that we have in the given molecular models. Okay, so let's start with part A here. And as usual, I just want to go and go over every single carbon in the molecule and see if they're connected to any functional groups. So starting with this carbon, this first carbon here, this is just CH3, so I'm not as interested, but we see that it's connected to an oxygen atom, right? So this whole part right here is our ether, right? And moving on with this carbon, sorry, let me box that again. Okay, so moving on with this carbon, it's only connected to other carbons and hydrogen, so I'm not as interested. Moving on with this carbon, that should be the same thing. But this next carbon right here, you see that it is connected with an oxygen atom, right? So this red sphere is an oxygen, so that represents our ketone, right? That represents our ketone, okay? And then moving on to the next carbon, we see that it is double bonded to the carbon next to it, so that would be our alkene. Okay? And they're both just connected to hydrogen atoms, so no other functional groups there. And moving on to our last carbon here, this last carbon, we see that it's only connected to hydrogen atoms, so there's no functional groups there either. So that's it for part A. We got 3 functional groups. We have an ether, a ketone, and an alkene. So part B now, again, just going through the carbons one by one. So starting with this carbon, right, we see that it has 3 hydrogen atoms, so no functional groups there. Moving on to this next carbon right here, we see that it is double bonded to a carbon, so that would be our alkene. Okay. Next, moving on to this carbon, only connected to hydrogen, so no functional groups. Next would be this carbon, and we see that it is connected to this structure right here, and this blue sphere represents a nitrogen. Okay, so now we got a nitrogen connected to 2 hydrogens, NH2, So this makes it our amine group. Amine. Okay. Last carbon here. Okay. Last carbon, we see that is connected. It is connected to two oxygen atoms, right? So this whole part right here is our carboxylic acid. Okay. Carboxylic acid. So those oxygens, those red spheres are oxygens, and there's this hydrogen atom right here. So that's a carboxylic acid. And at this point, we've gone over every single carbon in this molecular model for part B. So we ended up with 3 functional groups. We have an alkene, an amine, and a carboxylic acid. All right, problem 70. So we're still on drawing structures, and as you probably noticed, all our molecules here has a suffix of O8, or I guess not for part C, but O8 means we're dealing with esters, right? Okay, so let's go ahead and start. Part A, we got methyl pentanoate, so pent, meaning we have 5 carbons. So I'm going to go ahead and draw 5 carbons first. 1, 2, 3, 4, 5. And we have that O8, right? Got that O8, so meaning we have an ester going on here. So we're putting our ester here as carbon 1. Okay, so whenever you have an ester, the carbon connected to your oxygens would always be carbon number 1. So our countings would be like so. Okay, and we got methyl right here. So for esters, whenever we have a alkyl group connected, we always connect that to our terminal oxygen right here. So this is where our methyl would be. Okay, so all that's left for us to do here is to fill out those missing hydrogens, right? So carbon 5 is at the end, so it could handle 3 hydrogens. Okay, and carbon 4 would be CH2, same for carbon 3, and finally for carbon 2 as well. So we got all our hydrogens now, and you could go ahead and confirm by counting how many bonds you have on carbons, but I'll leave it right there. Okay, so part B, we got butanoate, meaning we have 4 carbons. So I'll go ahead and write 4, right? 1, 2, 3, 4. Okay, and O8, got this O8 again. So we have an ester. Okay, so we're gonna have something connected to that oxygen right there. Okay, so we have 2-methyl. Okay, 2-methyl. Let me use a different color. We got 2-methyl butanoate. So again, whenever you have an ester, the carbon connected to oxygens would be carbon number 1. And let's proceed counting to carbon 4. So we got 2-methyl, meaning we have a methyl group on carbon 2. Okay, so CH3 right there. Okay, and finally we have isopropyl. So meaning our oxygen right here is going to be connected to an isopropyl group. Okay, so isopropyl is just one of those structures that you need to memorize. So that is what an isopropyl group looks like. Alright, so all that's left for us to do is fill it out with hydrogens. Okay, so this would be CH3, CH2, oops, CH2. Carbon 2 here has one alkyl group connected to it, so meaning it can only handle one more hydrogen, okay? And carbon 1 already has all those 4 bonds filled out, so that would be our part B, okay? So I'll go ahead and let me write those parts just to make it clearer, okay? Finally, we got part C, okay? We got cyclohexyl acetate. So let's start with the acetate, okay? So an acetate is pretty much a kind of a nickname, sort of, for your ester with one more carbon connected to it. So what I mean by that is we have CH3 and then we have our ester. So that's it. That's all we have for an acetate. So whenever you have an acetate on your molecule name, this would be the kind of the base structure for it, okay? So that's your acetate, and we're told that it has a cyclohexyl group connected to it, okay? So as usual, that alkyl group would be connected to our oxygen, and I do have our cyclohexyl group right here that is ready to be connected, just right there, okay? So that's it. That is cyclohexyl acetate. Problem 71, we are still drawing structures, and this time we have amides. Okay, we're dealing with amides. So part A, we got 3-methyl pentanamide. So I want to start by drawing just 5 carbons for pent, right? So we got 1, 2, 3, 4, 5, and we have that amide, and I want to put that amide right here. Okay, so it's always going to be terminal, but as usual, just like in esters, this would be your carbon 1, okay? 2, 3, 4, and 5. Alright, and we're told that we have a methyl group on carbon 3, so let's go ahead and add that methyl group on carbon 3, okay? And at this point, we have all of our branch points or alkyl groups connected. All that's left for us to do is fill this out with the missing hydrogens, okay? So carbon 5 would have 3 hydrogens. Then we have CH2. Carbon 3 has 1 group connected to it, right? We have this methyl group, meaning it can only handle 1 more hydrogen. And then we got CH2 for carbon 2. And carbon 1 is already saturated. And then we have NH2 for our amide, okay? So that's for part A. Part B, we got phenyl acetamide, okay? So I want to remind everyone about acetate, okay? So whenever you see that acete, kind of like aceta, which is from acetate, so we could go ahead and draw an acetate molecule. So we got CH3, right? And we have an ester, okay? But because we have acetamide right here, this oxygen is going to be changed to a nitrogen, okay? So that would be acetamide. And then we have a phenyl group, okay? So unlike esters where alkyl groups are usually connected to the oxygen, here it's never connected to the nitrogen unless specified, okay? So the naming is going to be different if it is connected to nitrogen. So that phenyl group would be connected to this carbon 2 right here. So I'll go ahead and draw a 6-membered ring, okay? So there we go. That's our benzene ring right there. So we got phenylacetamide, and if you notice, since we added this bond right here, we have to reduce the number of hydrogens we have. Okay, so this carbon now could only handle 2 hydrogens, and as usual, this N right here could handle 2 more hydrogens. So there you have it. That's our phenylacetamide.
Hi everyone. Functional groups. Functional groups present in NaOH are okay, are first one is ester, that is C double bond O O. Then second one is amine. Of course, amine again. One is NH2, that is primary amine. The next one is tertiary amine. Then next functional group is aromatic ring. So the structure of alcohol and carboxylic acid used for synthesis of this, that is, this is NH2 C double bond O O C2H5, that is ethyl 4-aminobenzoate. Ethyl 4-aminobenzoate obtained from 4-aminobenzoic acid, plus another one is HOCH2 N C2H5. This is diethyl aminoethanol. Diethyl aminoethanol. Whenever they are treated with sodium ethoxide, C2H5O minus Na plus, you can say. So they give us NaOH NH2, then C double bond OO CH2 N C2H5 plus C2H5OH. So this is NaOH. It is also called procan. So these are the two structures of, one is alcohol diethylamine ethanol and second ethyl 4-aminobenzoate obtained from 4-aminobenzoic acid. Benzoic acid. Now 4-aminobenzoic acid cannot be used directly for synthesis of this, but that can be used in the form of ester.
Let's draw the structure of soap molecules, and this is a saponification reaction. So we have our reactants CH2 OC double bond O, CH2 14, CH3, CHO, C double bond O, CH2 7, CH double bond CH, CH2 7 CH3, and CH2O, C double bond O, CH2 16, CH3 plus 3KOH, and this is going to yield CH2OH, CHOH, CH2OH plus CH3, CH214, COO minus K plus, and CH3, CH2 7, CH double bond CH, CH2 7, COO minus K plus, and CH3, CH2 16, COO minus K plus. And that would be our saponification reaction between a fat, so this is our fat, potassium hydroxide, and we will produce an alcohol, which is glycerol, and a mixture of potassium salts. And these would be our 3 potassium salts breaking apart the fat.
Problem 74 is testing your memory of amino acid abbreviations, right? So I think this problem is pretty straightforward. It's just something that you have to memorize, right? So part A is SER. So there's really only one amino acid that starts with SER, which is serine, okay? So we have serine. Part B is THR for threonine. So threonine. PRO for proline. Part D is PHE for phenyl, right? Phenylalanine. And finally, we have CYS for cysteine. Okay? So hopefully that wasn't too hard for you and you've memorized your amino acids.
Problem 75, we are drawing amino acids. So for each of these parts, we have a requirement, and then we need to draw an amino acid that satisfies that requirement. Okay, so part A, we need an amino acid that contains an isopropyl group, right, which is underlined right here, isopropyl group. And before we start doing that, I want to go ahead and draw the base structure for an amino acid, right? We have this NH2 group right here, and it's connected to CH, and it's connected to carboxylic acid, okay? And below this middle carbon is where our R group is going to be, okay? Okay, so our R group has to have an isopropyl group, okay? So the easiest I could think of is valine, okay? So valine is exactly what that is. Valine is an isopropyl group, right, connected to this base structure for amino acid, okay? So that should be part A. That's not the only amino acid with an isopropyl group, but that's the easiest that came to my mind. Okay, next. Again, before we look at that, let's go and draw our base structure for amino acid. Okay, and then we're ready for our R group. So we need something that contains an alcohol group, okay? And the easiest I could think of is serine, because serine just has a CH2 group, and then it ends with an alcohol group, okay? So that's serine. Moving on to part C. Again, before we look at our requirement, I'll go ahead and draw our base structure. Okay, so now we're ready for that R group. We need one that contains a thiol group. So thiol is an SH group, and there's really only one, right? We only have cysteine. That's the only amino acid that has a thiol group. It's not the only amino acid that has a sulfur. Methionine has sulfur, but it's not a thiol group. It's not SH, right? Okay, finally we have part D. We want something that contains an aromatic ring. Okay, so let's go ahead and start with our base structure. And we want an aromatic ring, and the easiest I could think of is phenylalanine, right? So phenylalanine has this CH2, and then it has a benzene ring. Okay, and there you have it. Again, let's just go around and name these amino acids that we drew. So part A is valine, part B is serine, part C is cysteine, and part D is phenylalanine. Okay.
Problem 76, we are identifying amino acids, okay? So we are given this massive molecule right here, and we're asked to identify amino acids, okay? So what's nice about this molecule though, it's drawn in a way that we have our backbone in a straight line, right? And everything outside this box would be our R groups, okay? So those are R groups that's going to help us to identify our amino acids. And since we have 6 R groups, as you can count those blue circles, meaning we have 6 amino acids, okay? So I'll go and erase those blue circles to make it easier to see, and let's go for it. Okay, so our first group right here, okay, we have a CH, so we have a C connected to 2 more methyl groups, okay, and if you notice, it looks like a V, an upside down V, and that's how I remember the amino acid valine, okay? It looks like a V, okay? Next group right here, we have a CH2OH, okay? So I think this is just something you have to memorize. That would be serine. So you have 1 carbon and then it ends with a alcohol group. Okay. All right, then our third R group here is very unique. It has that phenyl group attached to it. So from phenyl, it has a phenyl group that tells us this is phenylalanine. And it gets that name because alanine only has CH3 as an R group, and then you connected a benzene ring to it, or you connected a phenyl group. So hence the name phenylalanine. Okay. Next, our fourth R group right here. As you can see, it has a sulfur, so meaning we could only have either cysteine or methionine. Okay, but since our S is in the middle of carbons, that means we have methionine. Okay, methionine. If it was cysteine, that S is gonna be the very end atom. Okay, so we're gonna have SH if it was cysteine. Next, we got this R group, and you see that it has alcohol in it. Okay, so if you have an alcohol in your R group, you could either have serine or threonine. Okay, so serine, as we already saw on this R group, it only has one carbon with it. Okay, so meaning this would be our threonine. Okay. And finally here we have a very simple R group. We just have a CH3, so that would be our alanine. Okay, so we have six amino acids on this molecule, and if it helps, let's go ahead and write it as one molecule. So we have valine, we got serine, we got phenylalanine, we got methionine, we got threonine, and finally we have alanine. Okay, so hopefully that was helpful. Problem 78. We're asked to name all the tripeptides possible, given methionine, isoleucine, and lysine. Okay, and my technique whenever we have this kind of problem is to just pick one of the amino acids to be the first amino acid in the chain. So let's choose methionine first. So I'll go right met for methionine. Okay, we're also asked to use the 3-letter abbreviations. So I'll follow that with isoleucine, and we got lysine left. Okay, and for the second tripeptide, I want to keep methionine as the first amino acid, and we have to flip lysine and isoleucine. Okay, so we got lysine as the second amino acid this time, and then we have isoleucine last. Okay, so next I want to have isoleucine as the first amino acid. Okay, so I'll have isoleucine right here, and then I have methionine and lysine left, so I'll just write methionine as second and then lysine. And then next I want to keep isoleucine being the second or the first amino acid, sorry. And then I still have methionine and lysine left, so this time I have to flip it. I need to put lysine as the second amino acid and then methionine as the last. Okay, and finally I want to have lysine as the first amino acid, so I'll put lysine. And then I have methionine and isoleucine left, so I'll just put methionine first, and then isoleucine would be last. And then again I want to keep lysine being the first amino acid, and this time isoleucine has to go second, and then methionine would be last. Okay, so there you have it. We have 6 tripeptides possible total, so we have 6 different combinations possible. Okay, so that's pretty much it. problem 79. We are given 4 amino acids here. We got alanine, serine, leucine, and glutamic acid. Now we are asked two things. One is how many tetrapeptides are possible. So how many different combinations can we have with these 4 amino acids? Of course, assuming you could only use each once, okay? And we are also asked to name 3 out of all those possibilities, okay? So we have this pretty neat formula for that. We got number of peptides, or a number of different possibilities, equals n factorial, okay? And n is the number of amino acids that you have. Number of amino acids, okay? So in case you don't remember what n factorial means, so let me explain that a little bit. So we got 4 factorial here, right? We got 4 factorial from having 4 amino acids, okay? So in math, that means we do 4 times 3 times 2 times 1, okay? So if you got 5 factorial, you're going to have to do 5 times 4 times 3 times 2 times 1, okay? So now that we have that, all that's left for us to do is solve that, which would equal to 24, okay? So there are 24 possibilities of combinations for these 4 amino acids, okay? So out of those 24, we're asked to name 3, okay? So I think it's pretty easy to come up with 3, right? So I'll just write what we have here in order. So we got alanine, right? And then serine, and then leucine, and glutamic acid. Okay? So that's for the first one. And then second, maybe I'll just rewrite the same thing and then flip the last 2, right? Glutamic acid and then leucine, right? And then I need one more. So maybe I'll flip the first 2, right? I'll get alanine. Oops. I just said I'll flip those first 2. So I'll have serine first, and then alanine second, and then I'll just go on with glutamine and then leucine, or glutamic acid, sorry. Okay, so that's it. We got 3 out of 24 possibilities, and I hope that was helpful. Alright, problem 80. Okay, we are asked to define the structural difference between an aldose and a ketose, okay? So right off the bat, we could see that these are sugars, okay? Because of the suffix OSE, so that's a suffix we use for sugars. And then what I have down here are 2 different structures of sugars, and this is not included in the problem. This is actually from a previous problem in the same chapter, but I thought they would be good examples for this problem. Okay, so we got the OSE, which stands for sugar, and then we got ald for aldose, and then ket for ketose. Okay, so aldose, from the prefix ald, that means we got aldehyde. Okay, means we got aldehyde. And then ket for ketose means we have a ketone. So that gives us our structural difference, right? An aldose would have an aldehyde, and a ketose will have a ketone. And so we look at our sugars here. We look at part A, and we see that does it have a ketone? No. Our carbonyl group here is at the end, and it's attached to a carbon and then attached to a hydrogen, which means we have an aldehyde. Okay, so this would be an aldose. And then we look at part B. Does it look like it has a ketone or an aldehyde? And it looks like it has a ketone, right? We have a carbonyl group in the middle, and then this carbon is connected to 2 other carbons, so that would be our ketone, and that means the sugar would be a ketose. Okay, so that is the structural difference between an aldose and a ketose. Alright, so for problem 35, we are on systematic naming. So we're asked to name these molecule models according to IUPAC rules. Okay, so starting with part A, we want to start with numbering our structure. So first we got to find the longest chain we could find, and then so let's start and do that. And I think from looking at it, I see that this would be my longest chain, right? And then I'll have 2 groups attached to it. Okay, and then we start counting from the end where the first branch point would occur. What I mean by that is, if we start counting from the right, we got 1, 2, 3, right? So the first branch right here, the first branch point would occur at carbon 3. But if we start counting from the left, we start with 1, 2, we see that the first branch point would be on carbon 2. So we got to start counting from the left because we want the branch point to occur first. Okay, so we want it to occur number 2 and not 3. So let's start counting from the left here. I'll go and erase everything I've got so far. Okay, so let's count from the left. We got 1, 2, 3, 4, 5. Okay, so we have 5 carbon chains. We have 5 carbons in our chain, and they're all single bonds, right? We don't see any double bonds, so that would be our pentane, right? That would be our pentane. Okay. Next is we figure out the branch points and see what we have connected. So for carbon 2, we see that we have a CH3, which means we have a methyl group attached. So that's going to be our 2-methyl, right? 2-methyl. And then next is we have, for carbon 3, right here, we have another methyl group coming out. So that's going to be 3-methyl, right? So since we have both methyl groups, we have to combine those, right? We have to combine these two and call it dimethyl. Alright, so now we've gone over all the branch points, and I think it's time to combine everything we have in here. Okay, so as far as numbering is concerned, we write 2 before 3. Okay, so we got 2, 3, and then we have dimethyl, right? Dimethyl pentane. Okay, so this would be your final answer for part A. So moving on to part B. Again, let's find the longest chain we could find before everything else. So from looking at it, I think this should be the longest chain, right? Actually, it doesn't matter, even if I counted this, and this would be the attached group. It doesn't matter. It will be the same amount of carbons in the chain. So we got 1, 2, 3, 4, 5, 6 carbons in the chain. But as you could see, the first branch point would be here, and also this is where our alkene is, so it's closer to the right side. Okay, so we need to start counting from this side. Okay, so let's go and erase everything we have so far and count from the right. Okay, so let's go for it. We got 1, 2, 3, 4, 5, and 6. Okay, so we have 6 carbons in our chain, and we have a double bond. So 6 would be hex, and since we have a double bond, that would be a hexene. Alright, so also the hexene, right, the hexene starts on carbon 2 right here, so we're gonna have 2 hexene. Alright, and also on carbon 2 we have our only group attached, right? We don't have any other branch points. This would be the only one, and we have a CH3, which is a methyl group. So we're gonna go ahead and write 2-methyl because it's found on carbon 2. Okay, so at this point I think we're done, and all we have to do is combine the information that we have. So as usual, we start with the attached group. So we have 2-methyl, 2-methyl, and then we have 2-hexene. Okay, so this would be our final answer for part B. For problem 81, we are classifying carbohydrates. Okay, so whenever we're classifying carbohydrates, we have 2 criteria. Okay, so one is it an aldose? Is it an aldose, or is it a ketose? Okay, that's question 1. And second is how many carbons? So number of carbons. Okay, so those 2 would be like our criteria for classifying carbohydrates. Okay, so let's start with part A here. So first question, does it look like it has a ketone or an aldehyde? Okay, so we have our carbonyl group right here, and we see that our carbon double bonded to O is connected to a hydrogen. So here we have an aldose. Okay, so that this is an aldehyde. So we have an aldose, and we name carbohydrates by starting with either aldo or keto. Okay, so this would be an aldo because it has an aldehyde. And next we count the number of carbons. Okay, we got 1, 2, 3, 4, and 5. Okay, so for 5 carbons we got the prefix pent, and we got that OSE, meaning we have a sugar. Okay, so that's just a suffix for sugars. So part A is an aldopentose. Moving on to part B. So again, we look at the carbonyl group. Does it look like it's an aldehyde or a ketone? Okay, so this is our carbonyl group, and I think it's pretty clear that it is an aldehyde. So that means we start it with the prefix aldo. Okay, and next is we count the number of carbons. Got 1, 2, 3, 4, 5, and 6. So for 6 we got the prefix hex, and we got that suffix OSE suffix for carbohydrates. Okay, so we got aldohexose. Part C. Let's look at our carbonyl carbon. This is right here, and since it is at the middle, that means we have a ketone, right? So we start our naming with the prefix keto. Okay, and then we count our number of carbons. 1, 2, 3, 4, 5, and 6. Okay, so we have 6 carbons in this sugar, meaning we have hex. We use the prefix hex, and again we've put OSE, meaning we have a carbohydrate. So part C is a ketohexose.
Problem 82 is asking for us to draw an open chain structure of a ketotetrose. Okay, so tetrose, meaning we have a sugar with 4 carbons in it, right? And then keto meaning we have a ketone as opposed to an aldehyde, okay? So I want to start by drawing just the 4 carbons. So 1, 2, 3, 4. Alright, and I just chose this carbon to be my carbon number 1, okay? So that would be our carbon number 1. And whenever we have a keto sugar, the carbonyl group is going to be on carbon 2, right? So I'm going to put it on carbon number 2. And then all the other carbons are going to have an OH group, okay? So they're all going to have an OH group. So let me add this OH group on this carbon, and then another OH group. So basically just an OH group for each carbon, okay? So this OH group is for this carbon. I just left some space there that we're going to need for the hydrogens, okay? So now we have all the oxygens that we need for this molecule. We could proceed to filling out the rest of the bonds with hydrogens, okay? So starting with carbon number 1, it's connected to carbon 2 here, and then the OH group, so it could handle 2 more hydrogens, okay? So it's going to be CH2OH, okay? This carbon 2, let me number our carbon so I don't confuse anyone. It's going to be 1, 2, 3, 4, okay? So that's the numbering for our carbons. Carbon 2 already has 4 bonds, so it's not going to have any hydrogens in it. Carbon 3 currently has 3, so it can handle 1 more hydrogen. And finally we have carbon number 4, which is currently connected to 1 carbon and 1 oxygen. Now, so it could handle 2 more hydrogens, okay? So obviously this space right here is not supposed to be there, so when you rewrite your molecule, just make sure you don't have that space. But this should be our open chain structure for a ketotetrose. Problem 83 is asking for us to draw an open chain structure of a 4-carbon deoxy sugar, okay? So before I even deal with this new term deoxy right here, I just want to go ahead and just draw that 4-carbon sugar, okay? And let's just deal with the deoxy part later. So I want to start with having those 4 carbons, right? 3, 4. And this sugar, I just chose to make it an aldose, okay? So that was just my personal preference. So I'm gonna have this aldehyde right here, okay? So that would be my aldose. And then if you have a regular sugar, you're just gonna have alcohol groups on all of the other carbons, okay? So let's actually go ahead and just add those alcohol groups on every carbon right here, right? And then we fill it out with hydrogens, okay? So every other bonds that are left shall be filled out with hydrogen. So carbon 1 is already is an aldehyde, so it's saturated, okay? The next carbon currently has 3, so it could handle one more hydrogen, okay? Same thing for this carbon, okay? And this this very last carbon right here could handle 2 hydrogens, okay? So deoxy, right? Term deoxy means we remove 1 oxygen, so just minus 1 oxygen, okay? Okay, so we have this, and usually it's the oxygen on the second carbon, okay? So we have to get rid of this oxygen, okay? And that oxygen is gonna be replaced by a hydrogen, okay? So that should be a 4-carbon deoxy sugar, and normally it would be expressed as just an H2 here, okay? We don't have to see that hydrogen separately connected like that. Okay, so instead of a CHOH, this changed into CH2. Problem 84. What is a fatty acid? Okay, so very straightforward. Basically, a fatty acid is just a long chain of carboxylic acid. Okay, so if you have a carboxylic acid right here, okay, then you're just gonna have a very long chain of that. Okay, so we could have maybe this is still your carboxylic acid part. Okay, and then you're gonna have that long chain with it. You could probably have some double bonds in there, right? So doesn't matter, but that is basically what a fatty acid is. Problem 85 here is asking what does it mean when we say that fats and oils are triacylglycerols? Okay, so what does that mean? So triacylglycerol is just a description of the structure of fats and oils. Okay, so this glycerol right here, so glycerol is a molecule in itself, and it looks like this. Got a CH2, got a CH, another CH2, and we got alcohol groups on all of that. Okay, so this is a glycerol molecule. Now triacyl, okay, triacyl means you have 3 fatty acids. 3 fatty acids. Okay, and as mentioned before, a fatty acid is just a very long chain of carboxylic acid. Okay, so I'm trying to draw it fast there, but that's what it looks like. Okay, and so since we have 3 fatty acid molecules, all those fatty acids would be connected to this part of the glycerol. Okay, so one fatty acid on this alcohol, one on this alcohol, and one on this alcohol. Okay, and as we react, of course, as you've probably seen in other reactions, that hydrogen is going to go away, and it's going to be connected to this carboxylic acid. So let's see what that looks like. Okay, so now that we've reacted our glycerol, that hydrogen is gone, and it's going to be connected to a fatty acid. Okay, have this one fatty acid chain right here. Okay, and then we'll have another one right here. This one's shorter and probably has a double bond. Okay, and then we have one more. Okay, so this one is a lot longer and has a lot more double bonds. Okay, so that's what it means when we say that fats and oils are triacylglycerols. It basically just describes this general structure right here. Okay, so problem 86, we are asked to draw glycerol myristate. Okay, and we are also given its components. We are told that it has a glycerol molecule and it has 3 myristic acid molecules. Okay, which I have in here. So this is the structure of myristic acid, which I got from a table in your book. Okay, so let's go ahead and try to draw this molecule. Okay, so we're starting with glycerol. Okay, so glycerol is just 3 carbons, right? Got 3 carbons right here, and they all have an alcohol group in there. Okay, so now that we have that, we have to react this myristic acid with glycerol. And if we react an alcohol with, let me change that. So if you react an alcohol with a carboxylic acid, you'll have an ester, right? So you'll have the C right here, and then you'll have your ester just like that. Okay, So this would be the carbon where the alcohol is. Oops. This is the carbon where the alcohol is, and this is where the carboxylic acid is. Okay, so we're gonna do the same thing with glycerol and myristic acid. So let me erase these alcohol groups for now and replace them with oxygen only. Okay, and now we're connecting it to our myristic acid. So again, we're gonna have that ester, right? We're gonna have that ester right there, and then we're gonna have that CH2, and we're gonna have 12 of those, and a CH3. Okay, and since we have 3 myristic acid molecules, that means each oxygen right here is gonna be connected to that myristic acid. Okay, so CH3, and one last connection here. CH2, 12, CH3. Okay, there we have it. That should be our molecule for glycerol myristate. Okay, problem 87. We are asked to draw the structure of spermaceti. Okay, and we're told that its structure is made out of cetyl palmitate, which is an ester of palmitic acid. Okay, and we'll explain a little bit more of that later. And so cetyl palmitate and cetyl alcohol, which is a 16 carbon alcohol. Okay, so what I have here in blue is cetyl palmitate. Okay, so it's an ester of two palmitic acid molecules. Okay, so palmitic acid, as you would see in your table, is a 16 carbon fatty acid. So as you could see, this is one of those palmitic acids, and this is the second one, right? This is the second one, and of course we're gonna lose some of those oxygens in the process. So this second palmitic acid right here doesn't have the oxygens connected to it originally. Okay, so that is our cetyl palmitate. Okay, this is the ester bond that the book is talking about. Okay, so let's clear that out a little bit. Okay, and next we have a cetyl alcohol, which is a 16 carbon alcohol. Okay, so it's just straight chain 16 carbons, right? So we have 15 CH2s and 1 CH3 at the end, and we'll have that alcohol group right there, just ready for our reaction. Okay, so if we react an ester with, this is an ester, with an alcohol, so what's going to happen is this oxygen is going to replace this oxygen, right? And this whole group right here is basically going to be kicked out. Okay, and this ester would be connected to this alcohol instead. Okay, so let's go ahead and draw it down here in our page. Okay, let me use green. So we'll have the CH3. So we'll have the first part of the ester, right? CH2, 14, and then we'll have this carbonyl group right here. Okay, so that is this part. Okay, and we'll connect it with this part. Okay, so we'll have the oxygen, and then we'll have the CH2, and we'll have 15 of those, and we'll have CH3. Okay, again, obviously this OH is gonna have to go. Okay, or this oxygen, but one of those is gonna have to go. All right, so this is actually our final structure here. This is the structure of spermaceti. For problem 88, we are asked to draw the isomers of a fat molecule, and we are given its components. So we have a glycerol, right? We have a glycerol, and we have 1 palmitic acid and 2 stearic acids. Okay, so what I have on the right here are the fatty acids that we need. Okay, so palmitic acid is a 16 carbon fatty acid, right? So it's this green structure right here that has 16 carbons. Okay, and stearic acid has 18 carbons. It's an 18 carbon fatty acid. Okay, and we have 2 of those, but this is what the structure looks like. Okay, so let's just draw one for now, and let's figure out the isomer later. So starting with glycerol, okay, we got CH2, CH, and another CH2, and all of those have alcohol groups, but I'm not gonna draw the hydrogens anymore because we know that when we combine it with fatty acids, that hydrogen is gonna have to go anyway. Okay, so we have 1 palmitic acid, so I want to go and just connect that with our first oxygen here on glycerol. Okay, so we're gonna have that ester bond. We're gonna have those 14 CH2s, right? CH2, and we have 14 of those, and we have CH3. Okay, and we have 2 of the stearic acids. So same thing for that. We got the ester, and then we're gonna have 16 of those CH2s, right? 16 and CH3. Okay, and we have one more. We have one more of that ester bond, and 16 CH2s and a CH3. Okay, so this is one of those. This is one of those isomers, and we have to think of the other one. And the only thing that I see that I could change here is the arrangement of our fatty acids, right? So instead of having these stearic acids right next to each other, I can move one of the fatty acids and move it on this top oxygen here, or top part of the molecule, I would say, and this palmitic acid would be in the middle. Okay, so let's try that. So again, I'm just exchanging these two. Okay, so again, starting with our glycerol molecule. Okay, I'll give us a little bit more space this time. And we have those oxygens. Okay, and we have the stearic acid first, so let's have that ester bond, right? And we have CH2, and we got 16 of those, and a CH3. Okay, and then we have the palmitic acid as our second ester bond here. Okay, CH2, got 14 of those, CH3. And finally, we have our last fatty acid, again another stearic acid. Okay, CH2, 16, CH3. Okay, and there we go, that we have our 2 isomers of this fat molecule. So problem 89 here is giving us this massive fat molecule, and it's asking for us to react it with KOH and give the products. Okay, so what we have here is a triacylglycerol. Okay, and whenever we're reacting triacylglycerol with a base, it makes a split like so. Okay, so probably not trying that, but it makes a split in this molecule, and what it does is it gives us back our components for a triacylglycerol, which is 1 glycerol molecule and 3 fatty acids. Okay, so let's go ahead and split this molecule. So we're splitting it right? So now we're going to have hydrogens on these oxygens, right? So these oxygens are going to be grabbing hydrogens. Okay, so now we have our glycerol and 3 fatty acids. So let's go ahead and name our products here. So we have a glycerol molecule, okay? And here we have an 18 carbon fatty acid, okay? We got 16 CH2s and we got 2 more carbons in here. So 18 carbon fatty acid with no double bonds is going to be stearic acid, right? So this is just information that you could find in your book, okay? So that's a stearic acid. Next we have a fatty acid with 1 double bond, okay? So that makes it our oleic acid. Oleic acid. Okay, and finally here we have this fatty acid with 3 double bonds. So it's got 3 double bonds, which makes it our linolenic acid. Linolenic acid. Okay, so there you go. That's all our products. Problem 90. What is a nucleotide? And we have to name its 3 components, okay? So a nucleotide is basically the monomer for nucleic acids, okay? So monomer for nucleic acids. So nucleic acids, namely DNA or RNA, okay? So it has 3 components, and what I have right here is a portion of a nucleic acid, okay? So let's look at this molecule and find the 3 components, okay? So here's one of its components. So we have a phosphate group, okay? So we got a phosphate, and then we also have an aldopentose, okay? So 5 carbon sugar, aldopentose, okay? So for DNA we have deoxyribose, and for RNA we have ribose. And as you could see with this sugar, we have this oxygen right here, which tells us this is an RNA molecule, okay? And lastly we have this amine base, okay? So we have adenine, guanine, cytosine, thymine, and uracil for RNA, okay? This specific one is adenine, okay? This one is adenine, but in general we have an amine base. In general we have an amine base, okay? So there's our 3 components. We have a phosphate, an aldopentose, and an amine base.
Okay, so for problem number 36, we're asked to identify the amino acid given the molecular model. Okay, so before we start, I want to remind everyone with the main chain for amino acids. We start with an amine group, and then we got a carbon, and then we have another carbon that is part of a carboxylic acid. Okay, so this is an amine group right here. And then this is where we would have our side chain, right? The other one would be a hydrogen. So the side chain is going to help us identify the amino acid. In fact, that's the only way we identify it when it comes to structures. Okay, so let's start with part A. Let's find that main chain, right? So here we have the blue sphere, which represents our amine group, and this would be our carboxylic acid. So that means this whole part right here would be our main chain. So that leaves us with this part being our side chain. So let's see what we have in our side chain. Okay, so we have a carbon connected to two hydrogens. So we have a CH2, right? And it is connected to an oxygen atom, and which is connected to a hydrogen atom. So we have an alcohol group. Okay, so we have CH2OH, which you probably remember is the side chain for serine. Okay, serine. Moving on to part B. Again, let's look for our amine group, which we see right here, and this part is our carboxylic acid, which means that this part would be our main chain for amino acid, and everything that's left would be our side chain. Okay, and in case you didn't notice, I actually didn't point it out. Here's the hydrogen atom connected to our carbon right here, right? So this hydrogen I'm boxing on the left represents this hydrogen, and same thing for part B. Here's that hydrogen. Okay, so everything outside the blue box here would be our side chain. So let's see what we have, right? We have ACH2 right here, right? And then we have another CH2, right? And then we have this yellow sphere, which represents a sulfur atom, okay? And finally, we have a CH3. Okay, so there's only two side chains with a sulfur. One would be a cysteine and one would be methionine. Okay, and as you probably remember, a cysteine would have an SH at the end, so the sulfur atom would be the very last atom. And we see here that we have a methionine because we have a methyl group after sulfur. Okay, so this amino acid would be methionine. Okay, so hopefully that was helpful.
Okay, so for problem 91, we are asked to name the sugars in DNA and RNA. Okay, so for DNA, we call the sugar deoxyribose. Okay, so deoxyribose, and I actually have the molecule right here to the right. So this right molecule is deoxyribose. Deoxyribose. Okay, so that's for DNA. And next is for RNA. RNA, we got the sugar ribose, which is actually this structure here to the left. So ribose. Okay, so what's the difference between the two? Well, there's only really one. Okay, an oxygen. That's it. Okay, so we have a ribose, right? You take away that oxygen, we call it deoxyribose. Okay, so that's the only difference. Nothing more, nothing less. Okay, and I hope that was clear. Problem 92 is asking for us to show the phosphate sugar bond in nucleic acids. Okay, so I just have the sugar here. This one is specifically ribose, and it already has the base attached to it. So now we just have to connect the phosphate group that we are missing. Okay, so there's going to be two phosphate groups attached to this molecule. Okay, so one would be here on the 5' carbon, right? So our phosphate is going to be connected to this oxygen, right? Let me actually just put it up. So this is where going to be our phosphate is. We're going to have that double bond and that single bond and so on and so forth. Okay, so this top part is going to be connected to another sugar. Okay, and then on the 3' end of this sugar, let me erase that part. Okay, on the 3' end, which is this part, I'll go and erase our hydrogen, right? And we are going to be connecting this oxygen to another phosphate group that is going to be a part of the next nucleotide. Okay, so here we're going to have our phosphate group, right? We're going to have this double bond right here. We're going to have this oxygen with a negative charge on it, and then there's going to be another oxygen, and this is where we're going to have our 5-membered ring, or our sugar. Okay, and so on and so forth. So this would be the second nucleotide at this point. Okay, but there we go, there's how phosphate is connected to our sugar here. Problem 93 here is asking for us to show the sugar amine base bond. Okay, so what I have right here is a phosphate group connected to our ribose here, and we have a uracil molecule here on the right, which needs to be connected to this sugar. Okay, so this uracil or amine base molecule is going to have to connect to the sugar, and where this arrow is pointing at is actually where this base is going to attach. Okay, so what I want to do here is to remove this OH group, right? So we're deleting that OH group, and we are connecting our base. Okay, so and the part of the base that is going to connect with the sugar is the nitrogen. Okay, so this carbon right here is going to be connecting to that nitrogen. Okay, so I'm not drawing the length of the bond to scale here because of just the constraints of our drawing, but this is where that amine base is going to connect. So there you have it. So problem 94, we are given a DNA strand, and we're just asked to give the complementary strand of this DNA. Okay, so just as a reminder, when it comes to DNA, G pairs with C and A pairs with T. Okay, so our first base here is a thymine, so that's going to be pairing with A pairs with T, C pairs with G pairs with C, and A pairs with T. Okay, so that should be our complementary strand. For problem 95, we are given the DNA strand, and we are asked to come up with the complementary RNA strand. Okay, and so before we go ahead and answer that, let's just go over the pairings for DNA and RNA first. Okay, so when it comes to RNA, it's just like DNA, G pairs with C and C pairs with G, right? And A, unlike DNA here, when it comes to RNA, A pairs with U, which is uracil. Okay, but T still pairs with A. Okay, so this would be if you have your DNA and this is the corresponding RNA bases. Okay, so let's go for it. We have this first base here, which is thymine. So again, thymine still pairs with adenine, right? So A, however, pairs with U when it comes to RNA. C still pairs with G, just like DNA. G pairs with C, and A again pairs with uracil. Okay, so problem 96, we have polypeptide chains, right? One of them has 21 amino acids and one of them has 30 amino acids. So there we go, 21 and 30. And we are asked how many nucleotides would be needed to code for each of these polypeptide chains. Okay, so this question is actually pretty straightforward. It's pretty simple. Okay, as long as we know that one amino acid, I'm gonna abbreviate it with AA. Okay, so one amino acid is coded by 3 nucleotides. Okay, let me write that. So one amino acid is coded by 3 nucleotides. Okay, so that's just the crucial information that we have to know. But now that we know that, okay, we have 21 amino acids, and in order to calculate the number of nucleotides needed, we just multiply it by 3, right? And the same thing for 30 amino acids, we just multiply it by 3, because again, 3 nucleotides are needed for 1 amino acid. Okay, so polypeptide chain with 21 amino acids would need how many? 63, right? Needs 63 nucleotides. And following the same process, 30 amino acids would need 90 nucleotides. Okay? And that's it. That's our final answer for this problem. Problem 97. We have sea urchin DNA here, and we are given its composition. Okay? So we are told that adenine comprises 32% of its DNA, and guanine comprises 18% of its DNA. And we're asked to calculate the percentage of thymine and cytosine in the DNA. Okay, so before we go ahead and do that, just wanted to mention that this information is irrelevant, right? We didn't have to know that it's a sea urchin. We just had to know that we're dealing with DNA. Okay, so I think it's very important to be knowledgeable of what information you need or you don't. Okay, so anyways, so we have adenine here, and I just wanted to remind everyone that adenine pairs with thymine when it comes to DNA, and guanine pairs with cytosine. Okay, so it's safe to assume that since A pairs with D and G pairs with C, A here is always going to have the same amount as D, right? For every A that you have in your DNA, you have the same amount of thymine. Okay, so if A comprises of 32%, then it's only logical to think that thymine would also comprise of 32% of DNA, right? And following that same logic, because guanine occupies 18% of the DNA, then every guanine would have a cytosine associated with it, then cytosine should also occupy 18%. Okay? And if you want to verify that information and see if you got the right numbers, you could go ahead and add all the percentages that we have, and all of these should total to 100%. Okay?
Let's draw the following compounds. For A, we have 2-methylheptane. So this would be a heptane, CH3, and a methyl group at carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, 2, 3, 4, 5, 6, carbon 7 for the heptane parent, 2-methylheptane. For B, 4-ethyl, 2-methylhexane, this would be CH3, CH, carbon 2, there's a methyl group, CH2, CH, carbon 4, there's an ethyl group, carbon 5, carbon 6. So there would be 4-ethyl 2-methylhexane. For C, we have 4-ethyl, 3,4-dimethyl octane. So carbon 1, carbon 2, carbon 3 is a methyl group, carbon 4 is a methyl group and an ethyl group, carbon 5, carbon 6, carbon 7, carbon 8. For D, 2,2,4 trimethylheptane, CH3, carbon 2, there are 2 methyl groups, CH, 2,4,4. Let's go backwards. Not 2,2,4. 2,4,4 trimethylheptane. So CH3, CH, so 1 methyl group, CH2, carbon 4, there are 2 methyl groups, carbon 5, carbon 6, carbon 7. There's my heptane 7 carbon parent. For E, we have 1,1 dimethyl cyclopentane. So draw cyclopentane, 5 carbon ring, carbon 1, 2 methyl groups. So there's 1,1 dimethyl cyclopentane. And for F, we have 4 isopropyl, 3 methylheptane, and this would be CH3, CH2, CH, carbon 3, we have a methyl group, carbon 4, we have an isopropyl group, carbon 5, carbon 6, carbon 7. And there would be 4 isopropyl, 3 methyl